Looking up at the stars makes you feel like the universe has been around forever. But what if we're living in a very specific time? What if we're living in a moment that's neither too early nor too late in the big picture of cosmic history? Time is like a big clock that keeps going from the explosion of the first stars to the stillness of space 1 trillion years from now. Are we at the start of life, the middle of it, or the end of it? Astronomy, physics, and the newest finds are showing us clues hidden in starlight, galaxies, and even the smallest particles. These clues could tell us exactly where we are in the story of the universe's history. How old is the universe exactly? Scientists have spent decades trying to determine the precise age of the universe, and the number that keeps coming back, confirmed by multiple methods, is 13.8 billion years. But what makes this number so solid today isn't just one measurement. It's the convergence of several independent techniques, each using very different parts of the cosmic story to keep time. That dim glow left over from the Big Bang is called the cosmic microwave background. It gives us one of the most important signs. This light came into being when the universe was only 380,000 years old. The shapes it makes look like sound waves going through the early universe. New telescopes, like the South Pole Telescope and the Atacama Cosmology Telescope in Chile, have made the most accurate readings of this light from a long time ago. Their most recent results show very small features in the polarization of the CMB that not even the Planck satellite could see 10 years ago. Scientists can figure out the past by estimating how these tiny ripples changed over billions of years. With an error range of only a few percent, they came up with the number 13.8 billion years. But researchers don't rely only on the light of the early universe. They also look at some of the oldest stars. Globular clusters, dense ancient groupings of stars, act as natural cosmic clocks. One of the most studied clusters, M92, has been calculated to be almost as old as the universe itself, close to 13.8 billion years. By comparing how bright these stars are to sophisticated computer models of stellar evolution, astronomers refine their estimates of how long they've been burning. The European Space Agency's Gaia telescope has improved this process by mapping star motions and distances with exquisite precision. Using this data, researchers have narrowed the age of the oldest stars to between 13.6 and 13.9 billion years, lining up almost perfectly with the CMB results. Another critical piece of the puzzle comes from the universe's expansion rate, measured by the Hubble constant. This number tells us how fast galaxies are moving apart today, and from that, scientists can work backward to figure out how long ago everything was packed together in a single hot, dense state. For years, there was a puzzling disagreement, often called the Hubble tension, between local measurements from nearby galaxies and global measurements based on the CMB. But recent observations from both the Hubble Space Telescope and the James Webb Space Telescope have brought these two methods closer together. Local measurements now hover around 70 kilometers per second per megaparsec, while CMB-based calculations are around 67, values close enough that, for age calculations, they no longer produce drastically different answers. There is still some debate, however. A few scientists propose that our Milky Way might sit inside a vast, low-density bubble of space, which could slightly change how we perceive the universe's expansion. If this local bubble idea proves true, it might shift the estimated age by a few 100 million years, but not enough to overturn the broader picture. The overwhelming agreement from all independent methods suggests the age really does hover around that 13.8 billion year mark. What makes this number so impressive is how different the methods are. One involves reading the faint glow of the universe's baby picture. Another involves studying the oldest stars that still shine today. And a third tracks the present motion of galaxies. All three approaches, with completely different physics behind them, converge on almost the same value. In science, that level of agreement is rare and powerful. This prediction is likely to get even more accurate with the help of new projects like the Simons Observatory and improvements to telescopes in Chile and Antarctica. These tools will make maps of the CMB that are more accurate and will be able to find tiny changes in the way light moves through objects in space. Also, better ways to use statistics to look at globular clusters are helping us figure out how old stars are by taking into account changes in helium content, dust, and even chemical mixes we don't know much about yet. The cosmic microwave background, a glimpse of time's birth. There would be no stars or galaxies if you could go back in time to when the universe was first formed. In every direction, you'd see a hot, glowing fog of energy. That faint glow is still there, though it has shrunk and warmed over billions of years. It's called the cosmic microwave background, CMB, and it gives us the best view of the very start of time as we know it. The CMB was released about 380,000 years after the Big Bang, when the universe finally cooled enough for electrons and protons to combine into neutral atoms. Before that, light couldn't travel freely because it constantly bounced off charged particles in the hot plasma. But once the universe became transparent, light escaped and began its 13.8 billion year journey to us. That ancient radiation is essentially the first picture of the universe we can ever hope to take, and it captures conditions just moments after the birth of time. The unique thing about the CMB is that it keeps tiny changes, temperature differences that are only millionths of a degree apart, scattered across the sky. In the early universe, sound waves moved through hot, thick plasma and left behind these patterns. As time went on, they show where matter was a little heavier or weaker. These are the first signs of galaxies, stars, and planets. There is a real sense that the seeds of everything we know are in this faint microwave glow. Modern telescopes have turned these ancient ripples into some of the most precise measurements in all of science. The Planck satellite set a high standard in the 2010s, but new observatories like the Atacama Cosmology Telescope and the South Pole Telescope are pushing further. They can now map not only the temperature, but also the polarization, the subtle twisting patterns in the CMB's light, at astonishing resolution. This polarization tells scientists how matter and energy moved in those first few 100,000 years and gives strong evidence for early cosmic inflation, the incredibly rapid expansion that shaped the universe in its first tiny fraction of a second. Every improvement in measuring the CMB sharpens our understanding of the universe's timeline. These maps don't just confirm the 13.8 billion year age, they also reveal how much of the universe is made of normal matter, and dark energy. For instance, careful analysis of the CMB confirms that dark energy began dominating the universe's expansion only a few billion years ago, a clue that we might be living in a transitional era rather than at the very end. Researchers studying the cosmic microwave background, CMB, are looking for very small patterns that might show signs of primordial gravity waves. These are ripples in space-time that were made when the universe first started. If they are found, they could give us direct proof of the exact conditions at the time of birth, which can't be found any other way. As of now, there has been no clear discovery, but tools are getting better at picking up on things. The first stars, Population 3's role in kicking off the clock. There were stars that were very different from the ones we see today long before the Sun, and even before the Milky Way formed its spiral arms. They are called Population 3 stars by astronomers, and even though we have never seen one, their marks can be seen all over the world. These were the very first stars to be born, and in many ways, they set the cosmic clock in motion. Before them, there was only darkness and gas that cooled things down. After them, there were light, heavy elements, and the building blocks for everything that would come. Population 3 stars formed roughly 100 to 200 million years after the Big Bang, in an era sometimes called cosmic dawn. The universe at this point was a simple mix of hydrogen and helium. No carbon, oxygen, or iron. That's a crucial difference, because the gas that makes up stars today cools and collapses, thanks to heavier elements acting as radiators. Without these metals, the first stars formed in very different conditions. Their gas clouds could not fragment as easily, so they grew far more massive, often hundreds of times the Sun's mass. Imagine stars so huge they could swallow our entire solar system. They lived fast and died young, some burning out in just a couple of million years. Why do these ancient stars matter so much? Because they were the universe's first factories of heavier elements. Through nuclear fusion, they forged carbon, oxygen, nitrogen, and other metals inside their cores. And when they exploded as supernovae, they spread those elements into the surrounding space. Every star that formed afterward, population 2 and the later population 1 stars like our Sun, was born enriched with these metals. Without that first wave of stellar pollution, there would be no rocky planets, no oceans, and no life. In a very real sense, population 3 stars switched on the clock for chemical evolution, setting the stage for everything we know. But how can we study stars that don't exist anymore? This is where smart science comes in. Population 3 stars haven't been seen directly because they died out billions of years ago, but their marks can be found in the oldest stars that are still around. Astronomers look for old stars in our galaxy that aren't very full of metal. These are called stellar fossils, and they were made from gas that was boosted by the first supernovae. Some of these old stars have very strange chemical patterns, like having a lot of carbon and almost no iron. This fits with what scientists have said about population 3 blasts. In a way, they are like messages from a time long gone. We are finally getting closer to seeing these first stars directly thanks to new technology. Already, the James Webb Space Telescope has found galaxies that were formed only 300 million years after the Big Bang. Some of these galaxies show signs of chemical ratios that could only come from population 3 stars. One galaxy, Sears 1019, has very strong signals for hydrogen and helium, but very weak signals for metals. This suggests that it may still be making first-generation stars. Future studies with Webb and the soon-to-be-built giant ground telescopes may be able to catch the light of these stars as they are still forming in very far-away young galaxies. Population 3 stars also played another key role. They likely triggered reionization, the event when ultraviolet light stripped electrons from hydrogen atoms, turning the once neutral universe back into a glowing, transparent one. Without this reionization, light would still be blocked by neutral gas, and the universe would remain hidden behind a cosmic fog. In that sense, the first stars didn't just give us heavy elements, they gave us sight. The clock image works well here because life and complicated structures hadn't really begun before population 3 stars. The universe was made up of nothing but gas growing into nothingness. These stars marked the point at which the universe changed from a smooth, easy soup to a place full of light, complexity, and hopes for the future. Every breath of air you take, every drop of water on Earth, and every grain of calcium in your bones all came from their short, violent lives. The current age of star formation. Are we past the peak? When you look up at the sky at night, the stars make quiet shapes that make you feel like you've been there forever. But the truth is that we live in a very specific part of the universe's history, where the birth of new stars is already slowing down. The universe isn't as full of stars as it used to be. Astronomers often say that our time is like a cosmic late afternoon. It's still bright and full of life, but it's not as bright as it used to be. The most busy and bright time in the history of the universe has ended, and now we are witnessing its slow but steady fall. Billions of years ago, the universe was dramatically different. Around 10 billion years ago, during an era called cosmic noon, star formation reached its highest point. Galaxies then were denser, richer in gas, and bursting with activity. Huge clouds of cold hydrogen collapsed rapidly under gravity, igniting star clusters in massive waves of creation. Some galaxies formed thousands of stars every year, filling space with young, hot blue stars that lived fast and died in spectacular supernova. Compared to that era, today's universe seems quiet, almost relaxed. Even star-forming giants like the Andromeda Galaxy or our own Milky Way are now forming only a handful of stars annually. Why the slowdown? The biggest reason is fuel exhaustion. After the Big Bang, galaxies were full of cold hydrogen and helium gas, but over billions of years, much of it has been used up. Massive stars burn through this fuel quickly, then explode, blasting gas out into space or heating it so much that it can no longer collapse to form new stars. Imagine a once dense forest after a huge wildfire. There's still life, but the easy fuel for big fires is gone. What gas remains in galaxies today is often too warm, too thin, or trapped in stable orbits, making new star formation far less efficient than before. Another reason has to do with dark energy and how the world is expanding faster and faster. A very long time ago, galaxies were much closer to each other and often crashed into each other, causing huge explosions of star formation as gas clouds hit each other. But these crashes between galaxies are happening less often because dark energy is pushing space apart faster. There are still some amazing mergers to come, like when the Milky Way and Andromeda will crash into each other in about 4 billion years. A starburst will happen for a short time because of that event, filling the sky with new stars. But these kinds of big events will happen less often as galaxies move farther apart, making the universe quieter with each new era. Today, the Milky Way forms just 1 to 3 stars each year, a modest trickle compared to the thousands formed in its past. Most of these are small, low-mass red dwarfs rather than massive blue giants. Red dwarfs are incredibly fuel-efficient, burning slowly for trillions of years, but they don't add much to the overall brightness of the universe. The dazzling, short-lived massive stars that once dominated the night skies of ancient galaxies are now rare. In a strange way, this calmer, slower time may be great for life. During cosmic noon, galaxies were very dangerous places because supernovae happened all the time and sent out deadly radiation that could kill off young planets. These days, stars are formed more slowly, and stable metal-rich stars like our Sun are made. For rocky planets to form with solid surfaces and complicated chemistry, this balance of metals and stability is very important. This age is thought by many scientists to be the best time for intelligent life to start because it is late enough for the universe to be adding the right elements, but early enough that there are still a lot of stars and galaxies. But this chance won't stay open for long. There will be almost no more star production in about 100 trillion years. By that time, almost all of the gas that is still out there will be locked inside stars or be too hot and spread out to fall. As stars die off, the sky will slowly get darker at night. After trillions of years, only long-lived red dwarfs will be visible, burning softly until they too die and turn into black dwarfs. So, have we reached the top? Of course. A very long time ago, the great age of star formation came to an end. We are now seeing a long, smooth slowing down, more like an afternoon in space than the start of the day. However, that also makes our time unique. It's not often that there are so many stars, planets, and energy and light in the world. Today is one of those times. The Sun's life clock. Where are we on its timeline? As if it had always been there and always will be, the Sun seems to last forever. It rises every morning and sets every night. But the Sun, like all stars, has a life cycle, and we are living in a very specific time in that cycle. In the grand scheme of things, our star is about middle-aged. Its core is quietly burning hydrogen, and it's neither too young and unstable nor too old and dead. Find out where we are on the Sun's life clock. This tells us not only about its future, but also about our future as a species, and even whether Earth will ever be habitable. The Sun formed about 4.6 billion years ago, born from a collapsing cloud of gas and dust enriched by earlier generations of stars. Like most stars of its size, it is a G-type main-sequence star, meaning it fuses hydrogen into helium in its core in a stable, long-lasting process. This phase of a star's life, known as the main sequence, is by far the longest and most stable period in its lifetime. For the Sun, this phase will last roughly 10 billion years, which means it's about halfway through its main sequence life. If we imagine the Sun's life as a 24-hour clock, we are standing almost exactly at noon. Stability is what makes this middle age so unique. Young stars often flare up without warning and send out strong radiation that can destroy planets' atmospheres or mess up the chemistry that life needs. The Sun, on the other hand, has found a steady beat. Its energy output is very steady, and compared to when it was young, its spin has slowed down. This means that it doesn't have as many violent magnetic storms. One reason life on Earth has been able to grow and thrive for so long is that it is stable. But being at noon also means the Sun is gradually changing. Even though it seems constant to us, the Sun's brightness is slowly increasing as it ages. Every 100 million years, its energy output rises by about 1%. Over the next billion years, this brightening will significantly affect Earth's climate, gradually warming the planet and potentially making it uninhabitable long before the Sun reaches the end of its life. Within 1 to 1.5 billion years, oceans may begin to evaporate, triggering a runaway greenhouse effect that will sterilize Earth, even though the Sun will still be firmly in its main sequence phase. The Sun will go through a stable middle age and then start its final act, where it will change greatly. It will run out of hydrogen in its core in about 5 billion years. This will make the core shrink and heat up, while the outer layers will grow. The Sun will get so big that it will swallow up Mercury, Venus, and maybe even Earth. It will turn into a red giant. Its surface will cool to a golden color, but it will be much brighter than it is now because of its sheer size. This will turn the inner solar system into a fiery, unusable wasteland. The red giant phase, though visually spectacular, will be relatively brief, lasting only a few 100 million years compared to the billions spent on the main sequence. Eventually, the Sun will shed its outer layers into space, creating a glowing planetary nebula that will enrich the galaxy with heavy elements for future stars and planets. What's left behind will be the Sun's small, dense core, a white dwarf roughly the size of Earth, but containing about half the Sun's original mass. This remnant will slowly cool and fade for trillions of years, eventually becoming a cold, dark black dwarf, a dead ember in the cosmic graveyard of stars. If you look at how habitable the Earth is, this middle-age stage is the best time for life. We are lucky to live in the Sun's past, which is the most safe and life-friendly time. If it happened too early, Earth might have been hit by a lot of energy from a younger, more active Sun. If it happened too late, the climate would get worse as the Sun gets hotter. This is a rare and short-lived middle act. In a few billion years, Earth will no longer be able to support complex life, but the Sun will still shine brightly for a while. It's amazing to think about how perfectly timed our lives are. The Sun is fully grown and calm right now, giving off enough energy for liquid water to grow on Earth. The solar system is also safe enough to support life. If there are civilizations billions of years from now, they will have to deal with a Sun that is much less merciful. By that time, Earth may not be livable at all. The rate of cosmic expansion, time speeds up as the universe ages. We feel like time doesn't change. Time moves at the same speed no matter where you are. A second is a second and a minute is a minute. On the biggest stages of the universe, though, time acts in a different way. The way we feel and learn about cosmic past is changing as space expands faster and faster. Galaxies are moving away from each other faster and faster. And the further into the future we look, the stranger this flow of time seems to be. Our world is expanding, which is changing not only the shape of space but also the way its time works. The story of this discovery began in the 1920s with Edwin Hubble. By measuring the light of distant galaxies, Hubble found that almost all of them are moving away from us, revealing that the universe is expanding. For decades, scientists assumed this expansion was gradually slowing down because of gravity, the pull of matter holding things together. But in 1998, two independent teams studying distant supernova made a discovery that stunned the scientific world. Instead of slowing, the universe's expansion is accelerating. Something invisible and mysterious, now called dark energy, is pushing space apart faster and faster. This speeding up growth changes more than just space. It also changes how we think about time in the universe. In the early universe, when galaxies were much closer together and the universe was younger, light could move more easily between them. Moving faster, galaxies are getting farther away, making it take longer for their light to reach us. When we look at those faraway galaxies, things that are happening there seem to move slowly because the light is stretched out and delayed. Time hasn't slowed down for the galaxies though. They are farther apart than ever. It's like cosmic time is being stretched out for faraway things, making the past of the world look like it's happening slowly when it's really moving quickly. The Hubble constant measures this expansion. Today, it's estimated to be between 67 and 70 kilometers per second per megaparsec, meaning every galaxy a million parsecs away, roughly 3.26 million light-years, is receding 67 to 70 kilometers farther every second. But it hasn't always been this way. In the early universe, gravity dominated, pulling matter inward and slowing the expansion. Dark energy only started to dominate around 5 billion years ago, flipping the balance. Since then, its influence has grown stronger, causing the expansion to accelerate with each passing billion years. The future will be very different from now if this trend stays the same. The galaxies we can see now will move so far and so fast that their light will never reach us again. This is known as crossing the event horizon of the universe. If there are any watchers left in trillions of years, they might look out and see nothing but their own galaxy floating in the dark. There would be no sign that any other galaxies ever existed. They will feel like cosmic time is moving more slowly because they will be able to see fewer and fewer new events. It will look like cosmic history stops, but it's really just speeding up. Some scientists have even speculated about a more extreme possibility. If dark energy grows stronger with time instead of staying constant, the universe could end in a catastrophic big rip. In this scenario, the accelerating expansion would eventually overwhelm all other forces. First, galaxy clusters would drift apart, then individual galaxies would be pulled apart, followed by stars and planets. In the final moments, even atoms and subatomic particles would be torn apart as space stretches infinitely in a finite amount of time. While this is only one theoretical model, it shows how deeply the expansion rate is tied to the universe's ultimate fate. But we are living in a unique time of change right now, the time when dark energy has just started to take over. If there had been intelligent life billions of years ago, they would have seen that the universe was still moving slowly because of gravity, with more galaxies merging and making stars. In billions of years, the sky will be much less full of galaxies, and future civilizations will have few to no galaxies to study because they will have faded beyond the cosmic limit. So does time really go faster as the world ages? In a way, yes. Not for us here on Earth, our seconds and minutes stay the same, but time is getting longer in the universe because it is expanding faster. It's getting harder to see big parts of the world because events are getting farther apart. The Stelliferous era, the age of stars, has an expiration date. Seems like the stars have always been there, and always will be when you look up at night. But stars aren't always there in the world. They are from a certain time in the past of the universe, the Stelliferous era, also called the Age of Stars. The universe is full of light, heat, and big things at this point in time. Stars are born, burn, and die. Still, it has a start, a middle, and an end, just like every other part of the universe's story. We are living somewhere in the middle of it, not at dawn, and not close to the end. The Stelliferous era began a few 100 million years after the Big Bang, when the first stars, massive metal-free population 3 giants, ignited and illuminated the cosmic darkness for the first time. These early stars burned intensely hot and lived short, explosive lives, enriching the universe with the first heavy elements. That single development, stars creating elements heavier than hydrogen and helium, set the stage for everything we see today: galaxies, planets, and eventually, life itself. Without this starry age, the universe would still be a cold sea of hydrogen and helium gas. Unfortunately, the Stelliferous era is only a short time. We're in the middle stages of it right now. Astronomers call the time when stars were being formed cosmic noon. It happened about 10 billion years ago. Back then, galaxies were full of cold gas, and the rate at which stars were born was very fast. Some galaxies made thousands of stars every year. That rate has slowed down a lot today. Every year, trillions of stars are still born, but most of them are small red dwarfs that last a long time, instead of big blue giants that only last a short time. These red dwarfs are the silent workers of the Stelliferous era. They burn their fuel so quickly that many of them will continue to shine for trillions of years, long after bigger stars like our Sun are gone. Yet even red dwarfs cannot keep this age going forever. The raw material for star formation, cold hydrogen and helium gas, is gradually running out. Every generation of stars locks more gas away inside stellar cores or blasts it into interstellar space, where it becomes too hot and diffuse to collapse again. Violent events such as supernova explosions and black hole activity heat and stir this gas, making it harder for gravity to gather it into new stars. Galaxies are steadily depleting their star-making reserves, meaning the era of bright star-filled skies has already passed its most active point. Astronomers estimate that the Stelliferous era will last for about 100 trillion years, an almost incomprehensible stretch of time compared to the universe's current age of 13.8 billion years. Over this vast timescale, star formation will continue to decline, dwindling to a mere trickle. Only rare bursts of star formation will occur, triggered by random galaxy collisions or pockets of gas that manage to cool and collapse. But by the end of this era, no new stars will ignite. The universe will move into its next phase, the degenerate era, where white dwarfs, neutron stars, and black holes will dominate an increasingly dark cosmos. But for now, we live in the golden age of stars, as many experts put it. Today, the night sky is full of many bright stars and galaxies that shine. This is a rare and short-lived sight. If people are still around billions of years from now, they will only be able to see the faint glow of dying stars because no new ones will have formed. In the end, the Milky Way and Andromeda will join into a huge spiral galaxy. This galaxy will slowly fade away as its stars age and die, leaving behind only black holes and the bodies of stars. Considering the possibility of life, this is a great time in the history of the universe. Too much chaos existed in the early universe, with huge radiation blasts and unstable conditions. It will be too quiet in the far future, with not many new stars growing and not many chances for new worlds with life. But there are still a lot of stars in the universe, and there are enough heavy elements like carbon, oxygen, and iron to make worlds like Earth. This is the only time when life as we know it can really grow, not just a time of light. The end of starbirth. How long until the cosmic night falls? When you look at the stars, you feel like the world is living. The stars seem like they've always been there and will always shine. That's just a trick of our limited view of time, though. The process of star formation, which has kept galaxies burning for billions of years, is slowly coming to an end. One day, it will stop totally. The Stelliferous era, the age of stars, will end at that point, and the universe will fall into a long, cold night that is sometimes called the cosmic night. It's not a question of if this will happen, but when. What time is it now? When will the universe's bright lights stop shining for good? Right now, star formation is still happening across the universe, but at a fraction of the rate it once did. Billions of years ago, especially during the peak of cosmic noon about 10 billion years ago, galaxies were busy stellar factories, fueled by enormous reservoirs of cold hydrogen and helium gas. Dense molecular clouds collapsed rapidly under gravity, producing clusters of massive bright stars. But that golden age has ended. Most of the gas that once fueled these starbursts has already been consumed, locked away inside stars, or blown out of galaxies by violent events. Supernovae, the explosive deaths of massive stars, have played a major role in this slowdown. When these stars end their lives, they release powerful shock waves and streams of radiation that heat surrounding gas or even eject it into intergalactic space, preventing it from cooling and collapsing into new stars. The same is true for supermassive black holes at the centers of galaxies. As they feed, they emit jets of high-energy particles and radiation, blasting star-forming material out of galaxies and into deep space. Over time, this process has starved galaxies of the cold, dense gas they need to keep creating new generations of stars. Even so, star formation hasn't stopped completely, just slowed dramatically. Most of the stars forming today are red dwarfs, tiny, faint stars that burn hydrogen slowly and live for trillions of years. Because they're so fuel efficient, they don't produce the same level of violent feedback as massive blue stars, meaning star formation can continue at a trickle for an astonishingly long time. Astronomers predict that isolated pockets of gas will keep collapsing into stars for up to 100 trillion years. But by then, the rate will be almost negligible compared to what we see today. The decline will be gradual, stretching across unimaginable timescales. In the next few billion years, galaxies will continue forming stars, but at an ever slower pace as they consume the last of their star-making material. Galaxy collisions, which are one of the last ways to trigger bursts of star formation, will become rare as dark energy accelerates the expansion of space. Galaxies will eventually drift so far apart that they'll never interact, cutting off one of the final sources of fresh star-making fuel. What little star formation remains will occur in isolated regions, quietly giving birth to dim red dwarfs in a universe that is already fading. The universe will look very different from what we know now by the time the very last star forms. We will no longer see the bright spirals and ellipticals that we see through binoculars. Instead, we will see scattered, faint groups of long-lived cooling stars. White dwarfs, which are the dead bodies of stars like the Sun, will turn into cold black dwarfs. Neutron stars will move away in silence, and black holes will be the biggest and heaviest things that are left. The world we live in now, which is full of bright stars, will have turned into a quiet cemetery of star remains. The degenerate era will then begin, which is a long cosmic night, during which no new stars will ever form. From where we are now, this future seems so far away. The universe is still very young compared to the 100 trillion years it will take for stars to stop being made. In a bigger picture sense, though, the fall is already happening. Each bright star in the sky is a part of a process that is slowly running out of fuel. Every galaxy we see now is a little less bright than it was a very long time ago. There are no more golden ages for star birthing. The universe is already moving toward its long night. This is a gift for us. The world is still full of light. There are still a lot of stars, and galaxies still shine brightly across space. We live in a rare and beautiful time. People who look into the future trillions of years from now, if they exist, will never see this view. They will live under a cool sky of ashes and won't be able to think that the universe used to be full of stars. The peak of heavy element formation. Are we in the best time for life? Things that were not there in the beginning of the world are necessary for life as we know it. In the first few seconds after the Big Bang, only hydrogen, helium, and a small amount of lithium were made. These elements are too simple to have been used to make planets, seas, or living cells. After that, carbon, oxygen, nitrogen, iron, and even the calcium in our bones were made in stars. These heavier elements, which are called metals in the field of science, have been slowly adding to the world. The interesting thing is that this process has a peak, and we may be living in the universe at just the right time for life to grow. The first stars, those massive population 3 giants, began enriching space with heavier elements when they exploded as supernovae. Each generation of stars recycled material adding more metals to the interstellar gas. Over billions of years, this created galaxies full of chemically complex clouds, which eventually formed rocky planets like Earth. But there's a delicate balance here. Too few heavy elements, and you can't form solid planets. Too many, and stars might burn too quickly or become unstable, flooding nearby planets with harmful radiation. Astronomers believe we live near the sweet spot of this chemical evolution. Our Sun, for example, formed about 4.6 billion years ago in a region with just the right metallicity, enough iron, silicon, and oxygen to build a rocky planet with liquid water, but not so much that the Sun burned out prematurely. In fact, studies show that stars with metallicities similar to the Sun are far more likely to host Earth-like planets. Too metal-poor, and you only get gas giants. Too metal-rich, and you often end up with giant planets that disrupt the formation of habitable worlds. This time frame also fits well into the past of the world as a whole. Making heavy elements reached its peak a few billion years ago, around the same time that the universe's stars were forming their peak. Back then, there were still a lot of big stars around. When they died, they blasted hydrogen into stronger elements and sent it flying into space. Today, the process of making stars has slowed down, but enrichment has hit a steady point where metal-rich stars like the Sun are widespread. If there is intelligent life out there, it might be because of this that it is most likely to appear now, not in the distant past or far future. It's interesting that too much time might actually make it less likely that someone will live. In a very long time, when there are only long-lived red dwarfs left, planets might still form, but they will circle stars with a lot less heavy elements, which makes it less likely that they will be complicated, rocky worlds. Also, older red dwarfs can be very active, putting out flares that remove planets' atmospheres, making them bad places for life to live. Right now, though, conditions are just about perfect. The universe has had enough time to build the ingredients for life, but hasn't yet moved too far into its slow decline. Many astronomers argue that this era, roughly 10 billion to 14 billion years after the Big Bang, is the most favorable time for life to appear. If civilizations exist elsewhere, they're probably evolving now, under stars that formed in the same chemical-rich era as our Sun. The age of galaxy clusters. Are structures still forming? The universe is not just a bunch of stars and galaxies spread out at random. Huge web-like structures are made up of strands of galaxies that stretch over unimaginable lengths and meet at the points where they meet. These galaxy groups are the biggest things in the universe that are held together by gravity. They look like towns on a map of the universe. But are these huge structures still being built? Or has the world reached its peak for building on a big scale? To answer that, we need to look back at how galaxy clusters came to be. Right after the Big Bang, the universe was nearly uniform, with only tiny differences in density. Some regions were just slightly thicker than others. Over billions of years, gravity amplified those small differences, pulling matter together into huge clumps. Dark matter, which makes up most of the universe's mass, played a crucial role here. It doesn't interact with light, but its gravity helped shape the skeleton of the cosmic web, forming deep gravitational wells where gas and galaxies would collect. The first galaxy clusters began to take shape around 3 to 4 billion years after the Big Bang. Back then, the universe was denser, and galaxies were closer together, making it easier for them to merge into larger structures. By the time the universe reached its star-forming peak 10 billion years ago, many of these clusters had grown into massive gravitational hubs, some containing thousands of galaxies. The Coma cluster and the Perseus cluster, for example, are ancient giants that likely started forming during that period. What about today, though? Galaxy groups are still forming, but much more slowly than before. The universe is 13.8 billion years old, and even though many of the biggest groups were put together billions of years ago, new stuff is still falling into them. X-ray cameras like Chandra and Erisita have shown that clusters are always eating smaller groups of galaxies and streams of hot gas. They take in new members slowly as gravity pulls stuff inward, making them almost like live things. But the rate of growth is different now. Dark energy, the unknown force that makes the universe expand faster, is slowly taking over. Space is getting bigger and bigger, and galaxies are being pulled apart faster than gravity can bring them back together. In the very far future, this means that cluster creation will pretty much stop. Simulations show that after 100 billion years, galaxies will be too far apart for new clusters to form because they will join or fall into current ones. This is a changing time, though. It's like looking at construction sites right before the end of a building boom when you study galaxy groups because they are still changing. Huge strands of gas and dark matter are still feeding into huge clusters, as seen by telescopes. For instance, the El Gordo cluster, which is one of the biggest and most powerful ever found, seems to have been formed when two very large clusters crashed into each other not long ago. Though not common, these kinds of impacts still happen in this day and age. They send shock waves through millions of light years of hot gas. Clusters also remain dynamic on the inside. The galaxies within them continue to merge, and their central supermassive black holes often flare to life as they feed on fresh gas. These black holes release enormous jets of energy, which heat the surrounding gas, and, in some cases, slow further star formation within the cluster. This balance between cooling gas and heating from black holes determines how long clusters remain active sites of star formation. From the perspective of life and observation, this era is perfect. We can still see other clusters because light from them hasn't been stretched beyond detection by cosmic expansion. Future observers, trillions of years from now, will not be so lucky. Accelerating expansion will eventually push most clusters beyond the cosmic horizon, making them invisible forever. They will be trapped in isolated island universes with no clue that the larger cosmic web ever existed. Dark energy dominance, a sign. We're in the transition era. Gravity has been in charge of everything for a very long time. It pushed gas into galaxies, shaped stars, and made the huge web of space that we see now. But in the last few billion years, something very big has changed. Dark energy, an unknown force, is now in charge of the fate of the world. Its rising power clearly marks a turning point in the history of the universe, and we happen to be living through it at the exact moment. Dark energy isn't something we can see or touch, but we know it's there because of how it affects the expansion of the universe. In the early days, gravity from dark matter and normal matter slowed expansion, pulling galaxies together. But about 5 billion years ago, the universe crossed a critical threshold. Dark energy overtook matter as the dominant force. Since then, instead of slowing down, the expansion of the universe has been speeding up. This transition is a big deal because it marks a clear before and after in cosmic evolution. Before dark energy dominated, galaxy clusters were still growing rapidly, gas was streaming into galaxies, and star formation was common. Now, galaxies are starting to drift apart faster than gravity can pull them together. Over time, this will shut down the formation of new large-scale structures entirely. What does dark energy really mean? In the field of physics, that is still one of the biggest puzzles. It could be a feature of space itself, like Einstein's old idea of a cosmic constant, which is energy that doesn't get less dense as space gets bigger. Other ideas are also possible, such as the one that dark energy changes over time, getting stronger or weaker as the world grows. If it gets stronger, the speed will speed up a lot, which could cause a future big rip in which galaxies, stars, and even atoms are ripped apart. The universe might slow down again in the long run if it gets weaker. The best information we have right now points to it being stable, but we can't be sure. We know we live in this transition era because of the way matter and energy balance out. About 70% of the universe's total energy today is dark energy, while normal and dark matter make up the remaining 30%. That balance didn't happen in the early universe. It's unique to this Middle Age cosmic epoch. Billions of years from now, dark energy will stretch galaxies so far apart that their light will never reach one another, locking the universe into isolated pockets. Billions of years ago, dark energy's effect was almost invisible compared to the overwhelming pull of matter. There is a rare point of balance right now, which has made some experts wonder if there is something special about this time. Not only because I'm interested in the idea, but also because I need to know. We can only look at galaxies and measure the effects of dark energy while galaxies are still visible. Most galaxies will be able to be seen in the far future because of cosmic acceleration. If there are civilizations in the future, they might not know that the world started, or that there are other galaxies. We're lucky to be alive now, where we can study these things. Recent observations from the Dark Energy Survey, the Euclid mission, and the James Webb Space Telescope are sharpening our understanding of this transition. Measurements of how galaxies cluster together and how light bends through gravitational lensing show that dark energy is behaving consistently with a cosmological constant so far. But these same observations also hint at slight irregularities that could suggest its strength changes very slowly over time. It's too early to know for sure, but scientists are watching closely. Being in this time of change also affects how stars form and whether they can support life. Since dark energy is just now starting to take over, galaxies are still close enough to sometimes crash into each other, which can cause starbursts. In billions of years, galaxies will not associate with each other nearly as much. That means we may also be living in one of the last great times for making stars and planets that are full of metals. This supports the idea that now may be the best time for life to thrive. The fate of galaxies. How long until Milky Way Andromeda merge? From where we are, the Milky Way seems to stay the same, a calm circle of stars where nothing major seems to happen. But in the grand scheme of things, our galaxy is not still. It is heading straight for its nearest big neighbor, the Andromeda Galaxy. Time is running out for a spectacular event that will change the night sky in a big way. When and how will it look are the big questions. Right now, Andromeda is about 2.5 million light-years away, but it's moving toward us at roughly 110 kilometers per second, faster than a commercial jet crosses Earth in an entire day. At this speed, the two galaxies are expected to collide in about 4 to 5 billion years. That may sound distant, but considering the universe is 13.8 billion years old, it's actually soon. For comparison, the Sun has roughly the same amount of time left before it swells into a red giant, meaning this galactic merger will happen just as the Sun nears the end of its own stable life. When people hear collision, they often imagine stars smashing into each other, but galaxies are mostly empty space. The distances between stars are so vast that direct star-to-star collisions will be extremely rare. Instead, gravity will dramatically reshape the structure of both galaxies. Their vast clouds of gas and dust will slam together, creating shock waves that trigger bursts of new star formation. Some of the brightest, most massive stars ever seen will likely be born during this starburst phase, briefly lighting up the merged galaxy with fresh clusters of blue giants. The event will be shown on a computer simulator. The first close pass will happen in 4 billion years. It will stretch both galaxies into long streams of stars. After a few more close calls over the next billion years, the Milky Way and Andromeda will merge into a single, very large spiral galaxy that is sometimes called Milkomeda. The Sun, and maybe even Earth, if it still exists, will be thrown into a new path that may be much farther from the center of the galaxy than the current one. What will this look like from Earth? If humans or their descendants are still here, the night sky will be breathtaking. A few billion years from now, Andromeda will appear as a growing swirl of stars, gradually dominating the entire sky. Over millions of years, the two galaxies will seem to stretch, twist, and eventually blend into a single, vast structure of stars. The merger will also mark a new stage in our galaxy's life. Right now, the Milky Way is still forming stars at a modest pace, and Andromeda is too. When they collide, the interaction will briefly revive star formation before eventually exhausting the last reserves of cold gas. After that, the newly formed galaxy will slowly fade as its stars grow old, entering the quiet phase that most elliptical galaxies already experience today. This event isn't unique to our corner of the universe. Galaxy mergers are common, especially in the earlier universe when galaxies were closer together. But as dark energy continues to accelerate cosmic expansion, such mergers will become rarer in the far future. Eventually, galaxies will be too far apart to ever meet, leaving isolated island universes. In that sense, we live at a special time, late enough that galaxies have grown large and mature, but early enough that major collisions like this can still happen. The Milky Way-Andromeda merger won't be the end of galactic evolution either. After the merger, the new Milky galaxy may eventually collide with smaller satellites like the Triangulum galaxy, adding more stars to its population. Over trillions of years, the remnants of these galaxies will settle into a calm, featureless mass of old stars and stellar corpses, marking the slow death of star-forming galaxies altogether. How long is it until the show starts? In about 5 to 6 billion years, the final merger should happen. The first close pass will happen in about 4 billion years. That seems so far away to us, but in the history of the world, it's almost right around the corner. Cosmic noon, the peak brightness of the universe. The night sky would be very different from what we see now if you could go back 10 billion years and look at it. There would be a lot more light in galaxies than there is now. Scientists who study the universe call that time cosmic noon. It was when the universe was brightest and star formation was fastest. Our universe is calmer, darker, and moving more slowly into its twilight now than it was during that golden age. Cosmic noon occurred roughly 3 to 4 billion years after the Big Bang, when the universe was just a quarter of its current age. During this era, galaxies were young, gas-rich, and colliding frequently. These frequent interactions compressed enormous clouds of hydrogen and helium, sparking intense starburst events. Massive stars formed in huge numbers, some hundreds of times heavier than the Sun, burning brilliantly and dying quickly as supernovae. A single galaxy at cosmic noon could form hundreds or even thousands of stars every year, compared to just 1 or 2 per year in our own Milky Way today. But it wasn't just the number of stars that made the sky bright during this time. It was also the kinds of stars that were being born. These starbursts were mostly made up of big blue stars. Their galaxies were filled with UV light from these huge stars that were millions of times brighter than the Sun. Their short, violent lives added heavy elements to the environment, making it possible for later worlds and life to form. But these huge stars also sent out strong winds and radiation, which finally started to blow away the gas that helped them form, which slowed down the process of stars forming over time. Galaxies themselves looked very different then. Observations from the James Webb Space Telescope have shown that many galaxies at cosmic noon were irregular and clumpy rather than graceful spirals. They were still assembling, rapidly pulling in gas from the cosmic web. Some of the brightest galaxies of this time were extreme starburst galaxies, forming stars up to 100 times faster than the Milky Way does now. The sub-millimeter galaxies detected at these distances are perfect examples. Massive, dusty star factories hidden in thick clouds that glow brilliantly in infrared light. However, cosmic noon did not last forever. A little over 8 billion years ago, the universe's fuel source started to run out. Less gas was stored in galaxies because a lot of it was locked up in stars or cooked to temperatures too high for it to fall back down. Supermassive black holes in the centers of galaxies also played a part. They sent out strong jets and winds that heated the gas around them, making it even harder for galaxies to keep up their high rates of star formation. The number of new stars started to slowly fall, and the universe began its long, slow fade into darkness. Today, we live in what could be called the universe's late afternoon. Star formation still continues, but at just a fraction of what it was during cosmic noon. Most stars forming now are smaller, long-lived red dwarfs rather than massive, luminous blue giants. These red dwarfs will dominate the future, but they will never make the universe as bright as it once was. The Milky Way and other galaxies have settled into more stable, calmer structures, no longer tearing themselves apart in violent collisions as frequently as they did billions of years ago. For life, this might actually be a good thing. Cosmic noon was dazzling but dangerous. Supernovae exploded constantly, flooding galaxies with deadly radiation. Today's calmer era, with stable, metal-rich stars like the Sun, is far more favorable for the formation of habitable planets. If intelligent life exists elsewhere, it is likely thriving now, not during that chaotic, blinding era. For now, though, the best show of stellar light is over. Astronomers think that the sky will get darker at night over the next few billion years as galaxies use up all of their gas. We're not just looking across space when we look at galaxies far away through powerful telescopes. We're also looking back in time to a time when the universe was brightest, a time we'll never live through ourselves. White dwarf, cooling, a countdown to cosmic darkness. Our stars won't last forever. Most of them will end their lives as white dwarfs, which are the burned-out cores of stars that used to be bright. These old stars are like old flames in the sky, slowly going out over unimaginable amounts of time. As they cool, they show how long it will be until the universe is completely dark. Studying them is like watching the clock in the universe tick away to a faraway time. A white dwarf forms when a medium-sized star, like our Sun, exhausts its nuclear fuel. After swelling into a red giant and shedding its outer layers, the star's core collapses into an Earth-sized sphere of incredibly dense matter. A teaspoon of this material would weigh tons, packed with electrons squeezed so tightly they form what scientists call degenerate matter. White dwarfs don't burn fuel anymore. They shine only because they're still hot from their previous life, glowing with leftover thermal energy. At birth, a white dwarf can be as hot as 100,000 Kelvin, glowing bright blue-white. But because it has no internal source of energy, it cools gradually over time, radiating heat into space. After billions of years, it fades from white to yellow, then to red, and eventually becomes too faint to see with ordinary telescopes. The Milky Way is already filled with countless ancient white dwarfs, some nearly as old as the galaxy itself, glowing faintly in infrared light. The rate of cooling depends on the dwarf's mass and composition. Carbon-oxygen white dwarfs, which are the most common, cool slowly, taking tens of billions of years to fade into near darkness. Heavier oxygen neon dwarfs might cool a bit faster, but all of them share the same fate. They will eventually become black dwarfs, cold, invisible husks that no longer emit heat or light. The universe hasn't been around long enough yet for black dwarfs to form, which is really astounding. After 13 billion years, even the largest white dwarfs still give off a faint glow. It will be about 1,000,000 billion years from now, a quadrillion years before the first real black dwarfs show up. That time will be very far into the universe's dark and quiet future, a long time after stars were first formed. White dwarfs are more than just cosmic fossils. They are also important tools for measuring time. Astronomers use their cooling rates, like natural clocks, to estimate the ages of star clusters and the Milky Way's disk. By studying the faintest, coolest white dwarfs in a group, scientists can determine how long ago the stars formed. This method helped confirm that our galaxy's oldest components are about 12 to 13 billion years old, providing a cross-check against other cosmic age estimates. New research suggests that some white dwarfs may not cool as smoothly as once thought. Crystallization, a process where the dense matter inside them solidifies into a crystal-like structure, releases extra energy, briefly slowing their cooling. Observations from the Gaia spacecraft have shown clusters of white dwarfs at similar temperatures, evidence of this crystallization phase. In the far future, As more dwarfs crystallize, the universe's fading light will linger slightly longer than models once predicted. But no matter how slowly they cool, the end result is the same: darkness. When the last white dwarfs finally fade into black dwarfs, the universe will enter a truly silent era. Only the occasional collision of stellar remnants or the evaporation of black holes will release bursts of energy, breaking the stillness. For any distant observers, if they exist, the cosmos will appear cold and empty, with no bright stars to guide their understanding of the past. But at the moment, white dwarfs are everywhere, quietly showing that time has passed. When you look at one through a telescope, you don't just see a dead star, you see how our sun will end. In 5 billion years, the sun will have grown into a red giant and then shed its upper layers. It will be left with a bright white dwarf that will slowly fade over trillions of years. It will be one more spark in the long march of the universe toward darkness. The half-life of protons, the clock that outlives stars. While stars may last billions or even trillions of years, protons, which are the very small building blocks of atoms, were once thought to be everlasting. Matter will still be around long after the last star goes out if protons really do last forever. However, more disturbing ideas from current physics suggest that protons might not live forever. They might finally break down, starting a countdown in space that will last long after all the stars, planets, and white dwarfs are gone. This proton clock might last longer than everything else in the universe. What does a proton's half-life really mean? Protons are amazingly stable compared to nuclear atoms, which break down in a predictable way. No one has ever seen a proton breakdown in any experiment that has been done so far. Theoretical physics, especially grand unified theories, GUTS, says that protons are not really fixed. These ideas say that over unbelievably long periods of time, protons can change into lighter particles like positrons and photons on their own, which would erase matter from existence. The predicted half-life of a proton is mind-boggling, at least 10 to the 34th power years. That's a number with 34 zeros. Some models push it even further, suggesting lifetimes up to 10 to the 36th power years, or more. For comparison, the universe today is only 13.8 billion years old, barely the first tick on this ultimate cosmic clock. Even if protons do decay, we're living in just the very earliest fraction of that timeline. Why do scientists think protons should decay at all? It comes from trying to unify the forces of nature. At extremely high energies, the strong, weak, and electromagnetic forces may merge into a single unified force. If that's true, protons, which are normally bound tightly by the strong nuclear force, could eventually leak through rare processes allowed by this deeper unification. Detecting proton decay would therefore be one of the strongest clues to the ultimate laws of physics. Large-scale studies are still looking for proton decay, even though it has never been seen. Huge underground detectors like Super Kamiokande in Japan and the soon-to-be-built Hyper Kamiokande are looking for the weak flashes of light that would happen if a single proton in the water broke down. The minimum lifetime keeps going up because there isn't enough proof yet. This proves that if decay does happen, it's very uncommon. But if protons do decay, the implications for the far future of the universe are staggering. Long after the Stelliferous era ends and star formation stops, long after white dwarfs cool into black dwarfs and black holes evaporate through Hawking radiation, protons would still be holding the last remaining structure of matter together. Only after quadrillions of times longer than the current age of the universe would this final clock begin to tick loudly. Matter will break apart once it does. As time goes on, planets, rocks, and even the remains of dead stars will slowly turn into clouds of light particles, leaving the world almost empty. Over stretches of time that are hard to understand, galaxies will disappear, not because they move away, but because the building blocks that made them up have broken down. Some theories propose that proton decay could release a final faint glow of energy even in the deep future, briefly lighting up an otherwise dark cosmos. This last flicker would be the final chapter of active physics, before the universe truly becomes a cold, featureless sea of particles. Now is what you might call the solid age of the universe. Protons are fixed, and there is a lot of matter around. If proton decay is real, we're in the very beginning of a very long period. This is so early in the process that it doesn't really matter what will happen next. But finding out if protons decay or not isn't just interesting. It's a way to find out if the world is really endless, or if even its most basic parts are doomed to disappear. How rare are intelligent civilizations? Timing and the Drake equation. When we look up at the stars at night, it's easy to picture many societies staring back at us from other planets. But do a lot of clever societies exist? Or are we just lucky to live in this time and place and be rare? Astronomers often use the Drake equation to answer this question. It is a well-known way to guess how many technologically advanced societies there might be in our galaxy. A new study shows that when life first appears in the history of the universe may be just as important as where it happens. The Drake equation breaks the question into steps. How many stars form? How many have planets? How many of those planets are habitable? How often life begins? And how often it evolves into intelligence? For decades we had to guess most of those numbers. But now, thanks to telescopes like Kepler and James Webb, many of the early terms are better understood. We know most stars have planets, and roughly 1 in 5 Sun-like stars might host a potentially habitable, Earth-sized world. But intelligent life requires more than just a planet in the Goldilocks zone. It also needs a stable environment, chemical richness, and time. And that's where timing becomes crucial. The early universe, for example, was hostile to life. For hundreds of millions of years after the Big Bang, there were no heavy elements to build rocky planets or the complex chemistry life needs. Even after metals began to spread, the first generations of stars produced extreme radiation and frequent supernova explosions that could sterilize young worlds. Intelligent life almost certainly couldn't have arisen during that chaotic era. Approximately 13.8 billion years have passed since the Big Bang. We're in a great place in the universe. Though the rate of star formation has slowed since its peak, galaxies are still calmer. There are still enough heavy elements to make worlds like Earth that are complicated. Our Sun is a great example. It was born in a place with lots of metals, so it was a stable, long-lasting energy source that gave life on Earth billions of years to develop. Models of statistics show that this could be the best time for civilizations to start forming in the past of the universe. It was too early, and the food wasn't ready. It will be too late. Star formation will have slowed down so much that there won't be many worlds that can support life. In fact, new research looking at a temporal version of the Drake equation suggests that intelligent life is likely to be grouped around this time. Most of the new stars that are being made right now are small red dwarfs. These stars will last for trillions of years, but they might not be good for life. A lot of red dwarfs send out flares that destroy planets' atmospheres or heat them up, making them dangerous for living things. Those middle-aged, metal-rich stars like the Sun might be the best places for worlds with life. So how many civilizations might exist right now? Estimates vary wildly. Conservative models say intelligent life might be extremely rare, perhaps only a few civilizations in the entire galaxy at any given time. Others argue that given hundreds of billions of stars, there could be thousands or even millions of civilizations, most of them too far away or too short-lived for us to detect. But even if intelligent life is rare, timing makes us lucky. We exist during one of the most favorable eras for habitability. This makes me wonder why we haven't heard from societies if they are popular now. This is the main idea behind the Fermi paradox, the fact that there is a high chance of life in the universe, but it is very quiet. There are also theories that have to do with time. Civilizations could rise and fall quickly, giving people only short periods of time to get in touch. Others may form much later, around red dwarf stars that last a long time. This means that most societies may not even exist yet. We might just be early, one of the first to show up in this age where people can live. The idea that we are early observers has a strange implication. If intelligent life becomes more common around stable red dwarfs in the far future, we might be pioneers rather than latecomers. But by then, the universe will look very different. Accelerating cosmic expansion will push galaxies beyond visibility, cutting off potential communication between star systems. Even if civilizations flourish trillions of years from now, they may never know other galaxies ever existed. The last supernovae. Are we near the end of big explosions? It's hard to believe that something so amazing can happen in the universe. When these huge explosions happen, massive stars die. For a short time, they shine brighter than whole galaxies and create the heavy elements that make planets, seas, and life possible. Even so, supernovae are more than just fireworks. They show that the universe is young and still busy. Supernovae are becoming less common as the birth of new stars slows down and the number of big stars drops. These titanic blasts will almost certainly go away one day. Are we already getting close to that calm future? Supernovae come in two main types. Core collapse supernovae happen when massive stars, usually more than 8 times the mass of the Sun, run out of nuclear fuel. Their cores collapse under gravity, triggering an explosive rebound that scatters heavy elements like iron, gold, and uranium into space. Type Ia supernovae, on the other hand, occur when a white dwarf in a binary system accumulates too much matter from a companion star and ignites in a runaway thermonuclear blast. Both types played essential roles in enriching the universe with elements necessary for planets and life. Billions of years ago, during the height of star formation around cosmic noon, supernovae were common. Massive stars were forming at furious rates, and since they live only a few million years, many were constantly dying in spectacular explosions. Galaxies then were filled with expanding supernova remnants, great bubbles of gas glowing in X-rays and visible light. Those ancient supernovae seeded the cosmos with metals, allowing later generations of stars to form rocky planets like Earth. But the rate of supernovae directly depends on how many massive stars are being born, and that rate has been falling for billions of years. Today, the Milky Way sees only about 1 or 2 supernovae per century. Many galaxies are even quieter, with long gaps between such explosions. This slowdown reflects the declining birth rate of massive stars. Gas-rich galaxies are running out of fuel, and new stars forming today are mostly smaller, long-lived red dwarfs that will never explode as supernovae. Type Ia supernovae, which come from older star systems, are still relatively common compared to core collapse events, but even their numbers will drop over time. As binary systems age and white dwarfs cool, fewer will reach the critical conditions needed for these thermonuclear blasts. In the far future, as star formation halts entirely, new supernovae will become extraordinarily rare. What does this future look like? Models predict that within a few trillion years, supernovae will effectively stop. The remaining massive stars will have long since died, and no new ones will replace them. The only flashes of brilliance will come from occasional collisions between stellar remnants, such as white dwarfs merging into rare late-time type Ia supernovae. But these will be few and far between, spaced over billions of years. Even now, we can see hints of this coming decline. Nearby galaxies like ellipticals, which finished forming most of their stars long ago, are already quiet and dark, with almost no supernova activity. They are a preview of what the entire universe will eventually become. Galaxies filled with old, dim stars and very little explosive drama. This fading of supernova also has profound implications for life and habitability. In one sense, fewer supernova mean fewer sterilizing radiation blasts that can strip atmospheres or trigger mass extinctions. But it also means fewer heavy elements being recycled into space, limiting the formation of new rocky planets and complex chemistry in future eras. In other words, supernovae are both destructive and creative, and their decline marks the end of the universe's most productive age for life. So, are big blasts almost over? We're not quite there yet, but we are well past the peak. The most amazing fireworks shows in the world happen much less often now than they did billions of years ago, and they will only get less common over time. In a few trillion years, the last great supernova will go out for a short time. In a world that is mostly dark, it may not be seen at all. Black hole growth. Are we in their golden era? People often think of black holes as monsters that hide in space and don't speak or change. But in fact, they grow, feed, and change over cosmic time. Some are very small and formed when stars collapsed, while others are supermassive black holes that are millions or billions of times heavier than the Sun. These huge objects are at the centers of galaxies and shape the space around them. They haven't always been this big. In fact, we may be living in the golden age of black hole growth, a short time in the history of the universe, when these huge gravity beasts are still producing matter. To understand why now is special, we need to look back at how black holes grow. Small black holes form early in a galaxy's life, often as remnants of massive stars. Over time, they collide and merge or pull in gas, slowly building larger black holes. But the real monsters, supermassive black holes, seem to have grown incredibly fast in the early universe. Observations from the James Webb Space Telescope have revealed surprisingly massive black holes just 700 million years after the Big Bang, far too soon for them to have grown so large by steady feeding alone. This discovery suggests that some black holes may have formed from direct collapse of huge gas clouds, skipping the smaller growth stages entirely. During the star-forming peak around cosmic noon, roughly 10 billion years ago, supermassive black holes fed at furious rates. Galaxies were dense, full of cold gas, and constantly colliding, funneling enormous amounts of material into their centers. When black holes feed actively, they become quasars, brilliant objects so bright they can outshine their entire host galaxies. Many of the brightest quasars we see today are ancient light from that era, revealing the chaotic growth of young black holes. But what about now? The universe is quieter than it was during cosmic noon, but black holes are still growing. Gas is scarcer, and galaxy collisions are less frequent, yet supermassive black holes continue to feed slowly in many galaxies, including our own Milky Way. The Milky Way's central black hole, Sagittarius A*, is relatively quiet today, but evidence shows it was more active in the past, leaving faint X-ray echoes in surrounding gas clouds. Other galaxies, like active Seyfert galaxies, still have moderately feeding black holes glowing brightly in X-rays and radio waves. At the moment, we may be living in the middle age of black holes, but for one reason, it's also their golden age. When galaxies crash into each other, the gravity pulls their center black holes closer together until they merge into one big black hole. Some of the strongest events in the universe happen when galaxies join. They send out huge gravitational waves that telescopes like LIGO and Virgo have only recently started to pick up. Future tools like the Laser Interferometer Space Antenna, LISA, will be able to detect mergers that are even bigger, which will show us how black holes are still putting together their mass. In the far future, however, this growth will slow dramatically. As dark energy drives galaxies farther apart, collisions will become rare. Gas supplies will continue to dwindle, and most black holes will spend the rest of cosmic history in quiet isolation. They will still grow slowly by swallowing nearby stars, or occasionally merging with other remnants, but the spectacular feeding frenzies of the early universe will be over. Eventually, in the degenerate era, black holes will dominate what's left of the cosmos, outlasting all stars before finally evaporating through Hawking radiation over timescales up to 1099 years. So yes, we might very well be living during the golden era of black hole growth, at least for the supermassive kind. We are late enough in cosmic history to study their mature forms and active feeding, yet early enough that galaxy mergers are still common enough to fuel them. Is the universe getting colder too quickly? Cosmic cooling rates. It was like a fire in the early universe. It was full of scorching radiation and particles that were so hot that atoms couldn't even form. It's a cold, almost empty space today, and the temperature of space itself is just above absolute zero. One of the most important changes in the past of the universe is this long process of cooling. But is the universe cooling faster than expected? If so, what does that mean for its future? Right after the Big Bang, the universe was unimaginably hot, trillions of degrees in its first seconds. As it expanded, it cooled rapidly. By the time it was just 380,000 years old, temperatures had dropped to about 3,000 Kelvin, allowing electrons and protons to combine into neutral hydrogen. This recombination released the first light we can still detect today as the cosmic microwave background, CMB. But the cooling didn't stop there. Over the next 13.8 billion years, as space stretched, the CMB's temperature steadily dropped from that 3,000 Kelvin glow to its current 2.7 Kelvin, only a few degrees above absolute zero. At first glance, that seems like an incredibly slow rate of cooling, but in cosmic terms, it's been remarkably rapid. The key reason is cosmic expansion. As the universe grows, light waves stretch, losing energy and cooling space itself. The faster the expansion, the faster the cooling. When dark energy began accelerating the universe's expansion about 5 billion years ago, it also started speeding up this cooling process. Now, every billion years, the CMB cools by tiny fractions of a degree, but over trillions of years, this acceleration will drive temperatures even lower, much faster than in the universe's early history. Scientists can track this cooling by studying how gas in distant galaxies interacts with the CMB. Quasar light, for example, passes through ancient gas clouds, and the way those clouds absorb light reveals their temperature billions of years ago. These measurements confirm that the cooling rate perfectly matches what we expect from expansion models. However, some recent studies suggest slight deviations in certain regions, raising questions about whether local pockets of space are cooling differently due to dense matter distributions or unknown physics. If confirmed, such irregularities might point to new aspects of dark energy or exotic particle interactions. Even though there are some small unknowns, the long-term trend is clear. The universe is moving toward thermal balance, which means that all of its temperatures are getting closer to the same number. In the very far future, as the expansion continues, the CMB will drop to 1 Kelvin, then 0.1 Kelvin, and finally close to absolute zero. This cooling will have big effects. As cold gas gets trapped in the remains of stars, star formation will slow down even more. In colder places, chemical processes that are necessary for life will almost stop completely. But is it cooling too quickly for life? In a sense, yes. The accelerated expansion caused by dark energy is shortening the time window for star formation and planet building. Billions of years from now, galaxies will be so isolated that no new material will mix, effectively freezing the chemical evolution needed for new habitable worlds. The current era may therefore be one of the best for life, not just because of metallicity and stable stars, but because the universe still has enough warmth and energy flow to sustain complexity. As for how long it takes for us to notice, the cooling is so slow that it won't happen for billions of years. What would we see if we lived trillions of years from now? The night sky would get darker, galaxies would fade, and space itself would get colder and emptier. People in the future, if they exist, will see the universe as a cold, quiet place that is very different from how it was when it was young and hot and busy. The neutrino background, a ghostly reminder of the beginning. Before the first atoms were made, and even before the cosmic microwave background lit up the universe, there was another thing left over from the Big Bang. It was the cosmic neutrino background, a sea of particles that is so weak that it is almost impossible to see. Unlike sunlight or even the CMB, these very old particles are almost impossible to see. They are like ghosts, sending messages from the very beginning of the universe. We could get a very close look at the beginning of the universe from them if we could measure them directly. Neutrinos are tiny, almost massless particles that interact so weakly with matter that trillions pass through your body every second without leaving a trace. They are produced in huge numbers during nuclear reactions, like those in the Sun or supernovae, but the ones that interest cosmologists are far older. These primordial neutrinos formed about 1 second after the Big Bang, when the universe was still an ultra-hot soup of particles. At that moment, the universe was dense enough that neutrinos collided frequently, exchanging energy with other particles. But as space expanded and cooled, they decoupled, freezing out of interactions and streaming freely through the cosmos ever since. The cosmic neutrino background, often abbreviated as CNB, is the oldest fossil of the universe we know of, predating the cosmic microwave background by hundreds of thousands of years. If we think of the CMB as the universe's baby picture, the neutrino background is more like its ultrasound, capturing an even earlier stage of its life. The problem is, detecting it is far harder than detecting the CMB. Neutrinos are incredibly elusive. They rarely interact with matter, and by now, after 13.8 billion years of cosmic expansion, they are extremely cold. Only about 1.95 Kelvin, slightly cooler than the CMB's 2.7 Kelvin. We have not yet detected the cosmic neutrino background directly, but its presence is indirectly confirmed. The way the CMB ripples, the distribution of galaxies, and the abundance of light elements like helium all fit perfectly with predictions that neutrinos were present in huge numbers early on. According to these models, there are about 340 relic neutrinos per cubic centimeter of space, meaning every cubic centimeter, including the space around you, is filled with these ancient particles silently passing through everything. Scientists are now developing ways to detect them directly. One of the most promising experiments is called Ptolemy, which aims to capture rare interactions between relic neutrinos and tritium atoms. If successful, it would give us a direct look at the very first second of cosmic history, something no other observation can achieve. Unlike photons, which were trapped in the early plasma until the universe cooled, neutrinos slipped free almost instantly, carrying information about conditions that no other signal can reveal. Some of the most important questions in physics might have answers in the neutrino background. Because of this, it might help figure out the exact masses of neutrinos, which is still one of the biggest puzzles in particle physics. Differences in mass, even small ones, can change how objects like galaxies were made. Relic neutrinos also change the general density of the universe, which in turn changes how fast it is expanding. If we could accurately measure them, it would help us get a better idea of how old the universe is, and might even point to new physics beyond the standard model. This ghostly background also serves as a warning that the universe we see now, with its stars, planets, and galaxies, was formed by particles that we can barely see. Neutrinos were speeding through space long before light could move easily. They took away energy and left behind small marks that changed how matter clumped together. The big picture of the world might look very different without them. Entropy's arrow. Are we climbing toward maximum disorder? The universe is always changing from ordered to chaotic. A basic idea called entropy tells us how things work. Ice melts, stars die, and galaxies spread out. The amount of chaos or randomness in a system is measured by entropy. In the world, entropy always goes up. This steady rise in entropy is sometimes called the arrow of time, and it's one of the strongest signs that our trip through space and time is one way. But where are we now on this path? Are we getting closer to the point of maximum chaos, or are we still going up? Right now, the universe is far from equilibrium, which is why we see so much activity. Stars burn brightly because there are sharp differences in temperature between their hot cores and cold space. Galaxies collide and form new stars because matter is still clumped together in dense regions. These differences drive the processes we see: heat flowing from hot to cold, gas collapsing into stars, and life using energy to grow. But as entropy rises, these differences are slowly vanishing, pushing the universe toward a state where everything is evenly spread out and no work can be done. the arrow of time began ticking at the Big Bang, which, interestingly, was a state of low entropy despite its extreme heat. At that moment, matter and energy were highly concentrated but incredibly uniform, meaning there was lots of room for entropy to grow. Gravity took advantage of that, pulling matter into clumps, forming stars, galaxies, and eventually planets. Counterintuitively, gravity increases entropy by creating these structures. Clumped matter has more ways to arrange itself than perfectly smooth matter does. Every star that forms, burns its fuel, and dies is another step in the universe's journey toward higher entropy. Where are we on our journey now? The scientists think we are still in the middle stages. The Stelliferous era, also known as the Age of Stars, is a busy changing period of time with lots of energy flows and exciting events. As they eat stars and gas, black holes, which create a lot of extreme entropy, are getting bigger very quickly. Supermassive black holes are now thought to have the highest entropy of any object in the universe, making everything else seem small. It is possible for a black hole to have more entropy than all the stars in the galaxy it is put together. But the hard part of the climb is still a long way off. There will be less and less noise in the world as stars die and gas runs out. This is called the degenerate era. White dwarfs, neutron stars, and black dwarfs will make up most of the system. Only a few exchanges will add energy to it. Black holes will eventually last longer than everything else and hold most of the chaos in the universe. When they finally disappear through Hawking radiation, which could take up to 10 years, they will send their stored entropy into space, which will move the universe closer to its final state. That final state is sometimes called heat death or maximum entropy, a perfectly uniform cold universe where no temperature differences exist and no processes can occur. No stars, no galaxies, no life. Just a thin soup of particles spread evenly across an ever-expanding void. We are nowhere near that stage yet. The current age of stars and galaxies is a relatively low-entropy, high-energy era, even though we've already traveled far from the extremely ordered beginnings of the Big Bang. The direction of time, which is connected to entropy, also helps us understand why we think time is going forward. We can remember the past, but not the future, because chaos is always getting worse. Boiling stars don't come back to life on their own, and eggs that have been broken don't get fixed. There might be no point to time in a world with greatest entropy because nothing will change. Hawking radiation timelines, black holes, outliving everything. People often say that black holes are like jails, where matter and light are locked up forever, but modern physics says otherwise. Stephen Hawking had a great idea in 1974 that helped us understand that black holes are not completely black. Over unimaginable amounts of time, they will slowly lose all of their energy in the form of Hawking radiation. Because of this process, black holes are not only the oldest things in the universe, but they are also the last things that have changed over time. By figuring out their dates, we can see into the faraway silent future of the world. Hawking radiation is a quantum effect. Near the event horizon, the invisible boundary of a black hole, pairs of virtual particles constantly pop in and out of existence. Normally, these pairs annihilate each other instantly. But if one particle falls into the black hole while the other escapes, it carries away a tiny amount of the black hole's mass as energy. Over time, this slow leak causes the black hole to shrink. The smaller it gets, the faster it evaporates, ending in a final explosive burst of energy. But this process is incredibly slow for large black holes. A stellar mass black hole, just a few times heavier than our Sun, will take about 10 to the 67 power years to fully evaporate. Supermassive black holes, the giants at the centers of galaxies with millions or even billions of solar masses, take far longer, up to 10 to the 99th power years or more. To put that in perspective, the universe today is only 13.8 billion years old. We are truly at the very beginning of the black hole era. During the coming trillions and quadrillions of years, black holes will dominate the universe, Long after all stars have died, white dwarfs have cooled into black dwarfs, and galaxies have stopped shining. Black holes will still be there, quietly consuming whatever matter drifts too close. They will merge occasionally, creating even larger black holes. But as the universe expands and matter thins out, even that activity will cease. In this far future, almost all matter will either be locked inside black holes or exist as isolated particles spread across space. When the world gets to the degenerate and black hole eras, the real show starts. Black holes will get smaller as Hawking radiation slowly eats away at them. The radiation will get hotter and brighter as it does this. The very end of evaporation will be very exciting. A black hole shrinks very quickly and lets out bursts of high-energy particles as it dies. The universe's last black holes, likely giant ones left at the centers of galaxies, will shine for a short time as the last major sources of energy before going away. Hawking radiation may also carry away information about what fell into the black hole, a question known as the black hole information paradox. Some physicists think the escaping radiation might encode subtle quantum details, which could help solve one of the biggest puzzles in physics, whether information can ever truly be destroyed. Future theories of quantum gravity might one day confirm this, but for now, it remains an open question. Black holes disappearing means that everything in the world is now over. When the last black hole goes away, there will only be a thin soup of photons, neutrinos, and particles floating around in a space that keeps getting bigger. There will still be time, but nothing important will happen. No stars, galaxies, or energy transfers. It will have reached its highest level of chaos, a state of calmness where time itself has lost all meaning. So, are we getting close to this point? Not even close. We live in the very beginning of the story of black holes. Black holes are still getting bigger. They eat stars, gas, and even other black holes to keep growing. We are seeing them at their best, not getting worse. But Hawking radiation makes sure that nothing, not even the strongest black holes, will last forever if the universe lasts long enough. The heat death clock. How far are we from ultimate equilibrium? The world is not only getting bigger, but it's also getting smaller. Entropy keeps going up because of all the stars that burn, galaxies that shine, and black holes that eat matter. Most cosmologists think that the universe will end in this slow drift toward heat death, which is a state of greatest disorder where there is no useful energy left. But how close are we to reaching this stable state? Even though the universe has been around for 13.8 billion years, the answer shows how young it still is. Heat death doesn't mean the universe gets hotter, in fact it's the opposite. It refers to the point when all energy is spread evenly across space, leaving no temperature differences to drive processes like star formation, chemical reactions, or even the motion of galaxies. In such a state, nothing changes because there's no usable energy left to do work. It's the ultimate quiet, where time itself loses meaning because nothing new ever happens. We're not even close to that sad state yet. There are still bright stars, galaxies crashing into each other, and black holes getting bigger. The Stelliferous era, the age of stars we see now, is one of the busiest and least chaotic times in the history of the universe. There are still huge amounts of free energy in the world, in the form of hot stars and thick gas clouds. But time is running out, and there are already signs that things will balance out. The first major step toward heat death will be the end of star formation. In roughly 100 trillion years, galaxies will have used up or locked away almost all their star-making gas. The night sky will grow darker as new stars stop forming, leaving only long-lived red dwarfs and cooling stellar remnants. Over time, even those will fade, transitioning the universe into the degenerate era, dominated by white dwarfs, neutron stars, and black holes. Next comes the black hole era, which stretches unimaginably longer. Black holes will slowly evaporate via Hawking radiation, releasing their energy into space over timescales up to 1099 years. These evaporating black holes will be the last sources of significant energy, creating rare flashes of light in an otherwise dark cosmos. Once the last black hole evaporates, no structures will remain. Only subatomic particles and low-energy photons scattered thinly across space. Finally, after all this activity ends, the universe will approach its heat death, also called the Big Freeze. Temperatures everywhere will approach absolute zero, and entropy will reach its maximum possible value. No chemical reactions, no fusion, no black hole activity, just a cold, thin soup of particles expanding forever. From the perspective of physics, the universe will still exist, but it will be functionally dead, with no energy gradients to sustain motion, life, or even the passage of meaningful time. In other words, how far away are we from this perfect balance? The big picture says that we are just at the beginning. We wouldn't even be at the first second if you tried to fit the whole future of the world into a single 24-hour day. Even though it seems like the age of stars has been going on forever, it is only the beginning of a story that will go on for unthinkable lengths of time. The time until heat death is very long, measured in trillions and trillions of years. Some parts of the process, like separation, happen faster though, because dark energy speeds up the growth. Galaxies are moving away from each other so fast that their light will finally go beyond what can be seen in the distance before heat death even happens. If there are still civilizations in a few trillion years, they will only be able to see their own galaxy and nothing else in the universe. When everything is finally balanced, the universe will already feel empty. At the moment, we are lucky to live in a time when stars, planets, and life are still around, but the world is still young and full of things to learn. The heat death clock is going off, but it's not even close to midnight yet. The universe still has a very long way to go before it reaches a perfect, quiet balance. Future star types, red dwarfs will outlive us all. When it comes to the world, stars are like the engines that move things around. Big blue stars burn brightly and die young, but red dwarfs live very long and steady lives. Really, they will last longer than any other kind of star. They will keep shining quietly for trillions of years after the last sun-like stars go out. These tiny stars will be the last lights in the universe when it gets dark and cold in the far future. To understand them is to look into the far future of the universe. Red dwarfs are the smallest, coolest, and most common type of star, making up about 75% of all stars in the Milky Way. They range from about 0.08 to 0.6 times the mass of the Sun, and are much dimmer, often invisible to the naked eye from Earth. But what they lack in brightness, they make up for in longevity. Their slow, efficient nuclear fusion allows them to conserve fuel far better than larger stars. While our Sun will exhaust its hydrogen in about 10 billion years, a typical red dwarf can burn steadily for 1 to 10 trillion years, and the smallest of them may last up to 20 trillion years or more. Why do they last so long? Larger stars burn hot, with fusion raging in their cores and outer layers, consuming hydrogen at a furious pace. Red dwarfs, on the other hand, are fully convective, meaning the hot material from their cores circulates throughout the entire star. This efficient mixing allows them to burn almost all of their hydrogen, whereas stars like the Sun only burn the hydrogen in their cores, leaving much unused. Essentially, red dwarfs sip their fuel rather than guzzle it. Their long lifespans mean that most red dwarfs that have ever formed are still alive today. In fact, not a single red dwarf has died of natural aging in the entire history of the universe, because even the oldest ones, formed more than 13 billion years ago, are still burning. When they eventually run out of hydrogen, they won't swell into red giants like larger stars. Instead, they'll grow hotter and bluer for a short time before shrinking into white dwarfs, quietly fading away over trillions of years. As bigger stars die off in the far future, red dwarfs will be the main source of light in the world. A very long time from now, when galaxies have used up all of their gas to make stars, red dwarfs will still be shining. They are the last natural lights that will shine before the world goes into a long, dark fall. When the last red dwarf star goes out, the universe will be well into the degenerate era, with only black holes and fragments of stars left. What about life around these very small stars, though? Red stars are some of the most interesting exoplanets to look for because they live for a very long time, giving life plenty of time to grow. In the habitable zones of red stars, many planets the size of Earth have been found. These include Proxima Centauri b and several worlds in the TRAPPIST-1 system. But living things near red dwarfs might have a hard time. Strong stellar flares can happen from these stars, which can wipe out planets' atmospheres or make areas very hot and dangerous. Some red dwarfs calm down over time, which might make the environment good for life, but it's still not clear if complex life can live there for billions of years. Still, in the long-term history of the cosmos, if life can adapt to red dwarfs, it might thrive long after sun-like stars are gone. Civilizations could potentially arise around these stars trillions of years in the future, long after our own species is gone. By then, the universe will be a much quieter place, with far fewer galaxies visible and star formation almost over. Intelligent life, if it exists then, might never know the universe was once bright and full of young, massive stars. The last star formed. When will it be born? Even though stars are still being born, each one is a sign that the universe is running out of fuel. Star formation has slowed down a lot since its peak billions of years ago, and it will stop for good one day. When that last star goes out, it will be the end of the Stelliferous era, which is the age of stars. But when will that last star really form, and what will it look like? Star formation depends on cold clouds of hydrogen and helium collapsing under gravity, but this raw material is being steadily depleted. Every time a star forms, it locks some of this gas into long-lived stellar remnants. Some gas gets recycled when stars explode or shed their outer layers, but with every generation, more of it becomes trapped in white dwarfs, neutron stars, or black holes. The process is slowing down dramatically as galaxies exhaust their gas reservoirs. At the peak of star formation around 10 billion years ago, the so-called cosmic noon, galaxies churned out stars at incredible rates. Today, starbirth is just a fraction of that, and most new stars are small red dwarfs rather than bright, massive stars. The Milky Way forms only about 1 or 2 stars per year now, and even that rate will continue to drop as gas runs low. When will the very last star form? Galaxy development models say that the number of new stars will slowly decrease over trillions of years. About 100 trillion years from now, the last stars should start to form. By then, almost all of the gas in galaxies will have been locked away or spread out too much to be able to collapse into new stars. As galaxies start to move away, star creation will stop altogether. The final stars born in this distant future will almost certainly be tiny red dwarfs, the smallest and most fuel-efficient type of star. These stars are incredibly long-lived, capable of shining for trillions of years. In fact, some of these last stars might still be burning long after the universe enters its degenerate era, when most stellar remnants have cooled into black dwarfs. The very last star in existence could continue to glow faintly, while almost everything else has gone dark. The conditions under which these last stars form will also be very different from now. In 100 trillion years, galaxies will not look at all like they do now. Most of them will have joined together to form huge circular galaxies. Other galaxies will have been pushed so far away by dark energy that they will no longer be observable. Stars will only form in very small areas of gas that are stirred up by small mergers or random gravity interactions. In a world that is mostly dark and quiet, the birth of the last star will be a quiet event. There won't be much going on in the last star's long life. It won't be as big and bright as the stars in cosmic noon. Instead, it will burn softly and slowly, use up its fuel for at least 10 trillion years before turning into a cold, dark cluster of stars. There will be no more stars after it dies. After this, the Stelliferous era will be over, and the universe will start its long fall. The idea that we are living so early in this big period is very interesting. Right now, galaxies are still bright. There are a lot of stars, and the night sky is full of light. In the future, societies, if any make it that far, will never have seen a world full of bright young stars. When they look up, all they will see are a few faint red points in the dark. They won't be able to imagine the bright, star-filled universe that was there before. Are physical constants changing over time? There are basic numbers that rule how the world works. These are called physical constants, and they include the speed of light, the gravitational constant, and the fine structure constant, which controls how light and matter interact. These factors are the building blocks of physics. They affect how stars shine and how atoms stick together. However, I would like to pose an interesting question. Are these factors really constant? Or could they be slowly changing over time? If they are moving, even just a little, it could mean that we are living in a new era of the world instead of one that is always the same. For decades, physicists assumed constants were fixed, unchanging properties of nature. But theoretical models, especially those that try to unify gravity and quantum mechanics, sometimes predict that these values might drift slowly as the universe evolves. Even a tiny change in these constants over billions of years could have huge consequences for how stars form, how life evolves, or even how long the universe survives. The constant that gets the most attention is the fine structure constant, alpha, which controls how strongly charged particles interact with light. If this value were just a little different, chemistry as we know it wouldn't exist. Atoms might not form stable bonds, stars might burn too fast or not ignite at all, and life would be impossible. Some theories of cosmology and string theory suggest that alpha might not be perfectly fixed, but could vary slightly with time or across different regions of the universe. So, do we have evidence for this? Astronomers have looked for signs by studying light from distant galaxies and quasars. Since light from these objects has traveled billions of years to reach us, it carries information about what physical laws were like in the past. By comparing the absorption lines of ancient gas clouds to those measured in laboratories today, scientists can test whether constants have changed. Most results so far suggest no measurable change, but some controversial studies have hinted at tiny variations in alpha on the order of a few parts per million over billions of years. If true, that would mean the laws of physics might not be perfectly universal. It has also been checked to see if other constants, such as the gravity constant, g, change. So far, accurate measures of the paths of planets, pulsars, and binary star systems have not found any changes. But even here, very small drifts might be too small for us to measure right now. Comparisons of atomic clocks are also pushing the limits of accuracy by seeing if basic factors change over much shorter periods of time, like decades or centuries. What does it mean for the future if these factors change? Over time, a slow shift could change the way the world works physically. For instance, if the fine structure constant went up too much, atoms could become unstable, which would stop chemistry and make it impossible to live. If the gravity constant got weaker, stars might stop growing a lot earlier than we thought. On even longer timescales, small changes could affect how dark energy acts, which could change the universe's final fate from a big freeze to something more dramatic, like a big rip or even a collapse. It's just as interesting to know if constants are really steady. That would mean that the rules of the world are set and never change. This would mean that there is a deep symmetry that holds true throughout time. A long time ago, no one could explain why the constants have numbers that are so well suited to life. Some experts say that we just happen to live in a lucky time when everything is right, while others say that if there are many worlds with different constants, we are in the one where life can start. For now, most of the data points to the fact that the constants we depend on are fixed, at least very precisely. The search goes on, though, because even the smallest proven drift would change how we think about physics and time. If future telescopes or tests find real changes, it would mean that the universe is changing not only what it contains, but also how it works. Cosmic acceleration. Could time's flow change in the far future? We feel like time is steady. What's a second? There is only 1 second, and clocks always go at the same speed. There is a strong link between time and the way space grows, and that growth is speeding up when we look at the universe as a whole. As dark energy pulls galaxies farther apart, some scientists wonder if this cosmic speeding up will change the way time moves in the very far future. We need to look at how time and growth are connected to understand this. Einstein's theory of general relativity says that time is not different from space. It is a part of space-time. Depending on where we are and how fast space-time is shifting, change in how we feel time can happen. This effect can already be seen in harsh settings. When viewed from the outside, time moves much more slowly near a black hole because of the way gravity bends space-time. On a much grander scale, growth does something similar, but not as obviously. Right now, the universe is expanding at an accelerating rate because of dark energy, which makes up about 70% of the universe's total energy. In the early universe, matter and radiation dominated, slowing expansion under their gravitational pull. But around 5 billion years ago, dark energy took over, and since then, galaxies have been moving away from each other faster and faster. This acceleration doesn't noticeably change how we feel time passing on Earth, but it changes how we measure cosmic time on a large scale. Light from distant galaxies is stretched, meaning we see ancient events slowed down, like an old movie playing in slow motion. What about the future? If dark energy remains constant, like a cosmological constant, the universe will keep expanding exponentially. Galaxies will slip beyond our observable horizon, and time will continue to feel normal locally. But from a cosmic perspective, events will look increasingly frozen. Distant galaxies will appear to move slower and slower as their light takes longer to reach us, eventually fading from view entirely. In effect, we'll be cut off from most of the universe's history, trapped in a bubble where time seems to pass normally, but with fewer cosmic events entering our horizon. Things could get much weird if dark energy changes over time, though. Dark energy might get stronger in the far future, according to some models. The speeding up would finally break galaxies, stars, planets, and even atoms apart in this case, which has been called the Big Rip. Since space expands faster than light, time might act in a strange way. In the last few seconds before the rip, time gaps might get very small, and things might happen much faster than someone looking in from the outside. This could lead to a catastrophic burst, in which even the most basic particles are ripped away in less than a second. On the other hand, dark energy could weaken or even reverse, which would slow growth down again. In these kinds of models, time would keep moving at the same speed, but the fate of the universe would change totally, which could lead to a big crunch or a cycle of birth and death. If that happens, cosmic time might start over with each new cycle, changing the direction of time's arrow every time it shrinks or grows. Even if dark energy stays constant, the far future holds some time-related surprises. Trillions of years from now, as star formation stops and galaxies fade, cosmic time will feel very different to any future observers. Without new events to mark the passage of time, the universe will grow increasingly static. In the far future, when black holes evaporate and only cold particles remain, time itself may lose practical meaning. Nothing will change, and without change, time becomes just a mathematical idea rather than a lived experience. How about in the far future? Could the flow of time change? Nearby, on planets, stars, or even galaxies, most likely not in a big way. In the big picture, though, time is already changing. As growth speeds up, it stretches it, slowing down events far away to a crawl and cutting off parts of space from each other. If dark energy changes, these effects could get a lot worse. Cosmic time could go from being very slow to a final rush or a slow freeze that lasts forever. The Big Rip possibility. Are we headed for a sudden end? Galaxy formation, star formation, and black hole growth have all happened slowly and gracefully over most of the universe's past. But some experts have come up with a much scarier idea for the future of the universe, the Big Rip. A heat-dead universe ends in a calm, cold way, but the Big Rip imagines an abrupt, terrible end in which space itself breaks apart. If this turn of events is true, the end will not be quiet. Galaxies, stars, planets, and even atoms will be destroyed. The idea of the Big Rip is based on dark energy, the mysterious force driving the accelerating expansion of the universe. Right now, dark energy seems to behave like a cosmological constant, meaning its strength stays the same as space expands. But what if it doesn't remain constant? If dark energy gets stronger over time, something physicists call phantom energy, its repulsive effect would grow until it overwhelms all other forces in the universe. Step by step, this is how the Big Rip would happen. Galaxies would start to move apart faster than gravity can hold them together in the early stages. This speeding up would get faster over time to the point where galaxy groups break apart. Then, galaxies would break apart because the stars inside them would no longer be held together by gravity. Planets would be thrown into space, no longer connected to their stars, as solar systems fell apart over time. But the most terrifying stage would come near the end, when the force of dark energy grows strong enough to overpower the electromagnetic and nuclear forces that hold matter together. Stars would be shredded into individual atoms, and finally, even protons and neutrons would be ripped apart in the last seconds of cosmic time. Space wouldn't just expand, it would stretch so violently that the very fabric of matter would disintegrate. How soon could this happen? That depends entirely on how dark energy behaves. Current observations, including data from the Planck satellite and supernova surveys, suggest that dark energy behaves like a cosmological constant, making the Big Rip unlikely. But our measurements aren't perfect. If dark energy's strength evolves, even slowly, the universe's future could be very different from what we expect. Some models predict a Big Rip could occur in as little as 20 to 30 billion years if phantom energy exists, though most estimates place it much farther in the future, if at all. Astronomers are actively looking for signs of whether dark energy is truly constant or changing over time. Projects like the Euclid mission and the Vera Rubin Observatory are mapping how galaxies cluster and how light bends as it passes through space, hoping to detect subtle shifts in the behavior of dark energy. So far, the data fits a constant dark energy model, but the possibility of phantom energy hasn't been completely ruled out. How would the last few seconds of a Big Rip feel? As time went on, if a smart society made it to that point, they would see their sky getting farther apart. Beyond the horizon, galaxies would disappear, stars would break apart, and in the very last few fractions of a second, even atoms would disappear. Since space and matter would be torn apart, time would end. But there's another way to look at this. If the Big Rip doesn't happen, the universe's fate will be much slower and quieter, ending in a cold heat death trillions of years from now. In that sense, the Big Rip is the fast-forward version of cosmic death, a sudden catastrophic finale instead of an endless slow fade. We don't need to be scared right now. Based on what we know so far, dark energy is steady and won't get stronger. However, the fact that we don't fully understand it means that there is room for surprise. Being able to change dark energy could mean that the world has a built-in timer that goes faster as time goes on. So, are we going to end all of a sudden? Most likely not, but we can't say for sure. The Big Rip is still one of the most exciting ideas about what might happen in the universe in the future. It shows that even space-time itself might not be as stable as it seems. The cyclic universe hypothesis. Are we early or late in a cycle? The usual view of the universe is that it started with the Big Bang and will end in some other way, like a heat death. But what if there is no real beginning or end to the universe? How about if it keeps being born, dying, and being born again? The cyclic universe hypothesis is a bold idea that time itself might be a part of a loop that keeps going around and around. It's not just how old the universe is that matters if that's true. The question is where we are in the cycle. Are we at the start of a new cosmic turn or at the end of another endless pattern? The idea of a cyclic universe isn't new. Ancient philosophies imagined eternal cosmic rebirths, and early 20th century physicists toyed with models where the universe repeatedly expanded and contracted. But modern versions are far more sophisticated, built on general relativity and quantum physics. One of the most discussed versions is the Big Bounce theory. Instead of starting from a singularity, the universe might have collapsed from a previous expanding phase, bounced at extreme density, and then expanded again. In this view, our current Big Bang was just one bounce in an infinite sequence. Another version, proposed by Paul Steinhardt and Neil Turok, involves cycles driven by higher dimensional physics, where our universe periodically collides with a parallel universe or brane. Each collision releases energy, triggering something like a Big Bang. Instead of expanding forever, the universe would eventually slow, contract, and reset in a new burst of creation. If this model is correct, we might be just one of countless generations of universes, each leaving behind subtle clues in the cosmic microwave background. Are there signs this could be true? Some researchers have searched for evidence of scars in the CMB, patterns that might remain from a previous cycle. While no clear proof exists yet, a few anomalies, like unusual circular patterns in the CMB temperature map, have been suggested as possible hints. They're controversial, but if real, they could mean we're not in the first universe at all. What part of the circle are we in now, if the cyclic theory is true? Stars and galaxies still rule the universe, which is only 13.8 billion years old. In cycle models, on the other hand, the growth stops after a while. Dark energy could weaken or turn around at some point, which would slow down and shrink the universe. If that happens, we'll only be in the first quarter or half of this cycle. There will be trillions of years until the next decline. If dark energy stays the same or gets stronger, on the other hand, the circle might be broken. Instead of a loop, we'd be living in a rare one-time growth. The circular view changes the way we think about the question of why we are here now. There was only ever one universe, so it's interesting that we live in the short, star-filled Stelliferous era instead of the much longer dark ages that are going to come. In a cyclic world, on the other hand, life might have many chances to show up at the right time during each cycle, making our timing less special. There is a chance that civilizations could rise and fall many times over many rounds, with no memory of the last cosmic turn. But not all physicists think that the world could be cyclical. The problem of entropy is one of the biggest ones. In theory, each cycle should make things less orderly, making each new world more stretched out and less pure than the last. Something must always set the entropy to a low number for cycles to keep going, but we don't fully understand how this works yet. Some models suggest that cosmic contraction could get rid of entropy in some way, but this has not been proven by an experiment. For now, the cyclic universe remains speculative, but it's not just fantasy. If future observations detect unusual patterns in the CMB, or if we discover that dark energy is slowly reversing, the idea will gain strength. Until then, we live in a universe that appears to be on its first and only run, expanding faster every day. So, are we early or late in a cycle? If the cyclic hypothesis is true, we're probably early. Only one bright chapter in an eternal series of rebirths. But if this expansion never reverses, we're not in a cycle at all. We're living in the universe's one and only story, heading for a final, irreversible end. The era of degenerate matter, white dwarfs and neutron stars everywhere. The world we know today is full of bright galaxies, stars that shine, and nebulae that glow. The good times will end soon, though. It will be a long time before there are any more new stars. After that, the universe will be ruled by the dead remains of old stars. The stars will be full of white dwarfs, neutron stars, and black dwarfs during this time, which is called the era of degenerate matter. It will be like a graveyard of stars, full of dead things that have been dead for trillions of years. White dwarfs, the remnants of medium-sized stars like our Sun, will dominate this era. At first, they will still shine faintly, slowly radiating their leftover heat. But as time passes, they will cool and fade into black dwarfs. Dark, cold, Earth-sized husks made mostly of carbon and oxygen. None exist yet, because even the oldest white dwarfs haven't had enough time to cool completely. The first black dwarfs won't appear until trillions of years into the future. Neutron stars, which are made when the cores of massive stars crash, will also stay. They will be spread out across the sky like frozen lighthouses. These very dense objects, which are only a few kilometers across but weigh more than the Sun, will also get cooler and less bright. Some may spin very quickly for billions of years and send out weak radio waves, but finally they will stop. A few paired neutron stars might occasionally crash into each other, sending out short bursts of energy, but these events will happen less often over time. During this era, the night sky will look nothing like it does today. No bright stars, no glowing nebulae, just faint red embers scattered sparsely among a growing darkness. Galaxies will still exist, but they will be quiet and dim, made up almost entirely of stellar remnants drifting through vast, empty space. Still, even though this time seems to have no life, some things will still be done. Sometimes, remains of stars will crash with each other because of gravity, creating brief bursts of energy. For instance, if two white stars merge, nuclear fusion could start up again for a short time, causing a faint late-time supernova. Even if neutron stars join, gravitational waves could still be sent through the dark universe. But these events will happen very rarely, with billions or even trillions of years between them. It's possible that the era of degenerate matter will last a very long time. Some red dwarfs, which are the tiniest and oldest stars, will keep burning hydrogen slowly for a lot of this time. A lot of them will last for trillions of years, giving the world its last natural light. They will die though, and it will be almost completely dark after that. As the era progresses, gravity will keep reshaping galaxies. Stellar remnants will occasionally spiral into black holes, feeding them and slowly increasing their mass. Over time, black holes will dominate the universe as the largest and most massive objects left. But even they will eventually begin their own slow decline, evaporating through Hawking radiation over timescales so vast they make the era of degenerate matter look brief by comparison. If people ever look back into the past, they will see a world that seems very old and still. There won't be any bright young galaxies to study, and there won't be any new stars to power life. The cosmic graveyard will be empty and quiet, with only the cold, decaying remains of what used to be a bright universe. The last chance for habitability. Are we in the best epoch? Life has not always had it easy in the world, and it never will. Sometime in the past, very few times, it seems like the conditions are just right for habitable planets to form, for life to develop, and for advanced societies to thrive. According to many scientists, we are now living in a sweet spot in time. This is a great age for life that will never happen again. But why is now the best time? Also, how long is this window open for? Life as we know it requires three crucial ingredients: stable stars, planets rich in heavy elements, and a relatively calm cosmic environment. All three depend on timing. In the early universe, shortly after the Big Bang, none of the elements needed for life existed. The first stars, the massive population 3 giants, contained almost no metals. In astronomy, any element heavier than helium is called a metal. Without metals, rocky planets like Earth couldn't form, and even if they could, the violent radiation from early starbursts and frequent supernova would have made them inhospitable. It took billions of years for the universe to enrich itself with heavy elements. Each generation of stars forged metals in their cores and spread them into space through supernova explosions. By around 8 to 10 billion years ago, the metallicity of galaxies had reached the level where stable, rocky planets became common. Our own Sun, born 4.6 billion years ago, is a perfect example of a second-generation star with just the right chemical balance for habitability. Enough metals to form Earth-like worlds, but not so many that the star burns out too quickly. Because the universe is stable, timing is also important. Galaxies were a mess during cosmic noon, the time when the most stars were being formed. There were huge starbursts, black holes, and a lot of radiation. Even if planets existed, these places were not good for life. After billions of years, the process of making stars has slowed down, and galaxies are now peaceful. There are still supernovae, but they don't happen as often. This means that high-energy blasts are less likely to kill all living things. Then why is this the best time? Because we are at a unique point in time. The universe has made enough heavy elements to make worlds like Earth widespread, and the space environment is calm enough to let them stay stable for billions of years. If there are intelligent societies, they are most likely to have formed during this middle period, which is about 10 to 20 billion years after the Big Bang. There may be other societies out there, but if they are coming into being now, not much earlier or much later. What about the future? Star formation will continue for trillions of years, but it will be dominated by red dwarfs, the smallest, longest-lived stars. While they are stable, they may not be as friendly to complex life. Many red dwarfs emit powerful stellar flares that can strip planetary atmospheres or bathe surfaces in harmful radiation. Even if life does adapt to such conditions, these planets may lack the same stable, Earth-like environments we enjoy. Also, because the number of stars being made is going down, fewer new worlds will form in the future. As galaxies run out of cold gas, the number of worlds that might be livable will drop sharply. When stars stop forming fully in about 100 trillion years, no more worlds that people can live on will be born. Around long-lived red dwarfs, life will have to be able to stay alive by then or not at all. In that sense, we may truly be living in the last great age for habitability. We are late enough in cosmic history to have metal-rich stars and planets, but early enough that galaxies are still forming new stars and recycling heavy elements. Future life might be possible, but the odds will keep shrinking as time moves on. The golden age of Earth-like worlds won't last forever. Are we now living in the most favorable era for life? All the evidence points to yes. We live in a unique time when the universe is just fully grown enough for life to exist, but not quite there yet, where it will slowly fall apart into darkness. For now, the stars are still shining, planets are still forming, and there are lots of good conditions for life. However, this window is ending, and the world will not be as friendly in the far future. Are we at the midpoint of cosmic light? The universe is very bright now compared to its very distant past and future. It is full of stars, galaxies, and clouds that shine across billions of light years. The good times will end soon, though. Light has a past. It reached its highest point and will finally go away. Where are we in that story now? Are we still going up, or have we reached the middle of the universe's light output? Astronomers now think that things are going downhill and that we are living in a twilight age instead of the bright past. You can tell how much light there is in the world by how many stars are burning and how quickly new ones are being made. A few 100 million years after the Big Bang, the universe was very dark, with only a weak glow from the cosmic microwave background. Then, when the first stars came out, galaxies lit up, starting a long period of getting brighter. Cosmic noon is the name for the time when the peak happened, which was about 10 billion years ago. Stars were being made more than 10 times faster back then than they are now, and huge blue stars burned brightly before exploding in amazing supernova. There would have been a lot more light in the sky at night if you could have been on Venus back then. Since then, the light has been slowly fading. Star formation has declined drastically over the last several billion years as galaxies have consumed or heated up their star-forming gas. Today, most new stars being born are long-lived red dwarfs, which are faint compared to the short-lived, brilliant blue stars of the past. Even though the total number of stars in the universe is still increasing slightly, the combined brightness has already passed its peak and is declining steadily. In fact, studies measuring the total light output of galaxies show that the universe is now producing only about half as much visible and ultraviolet light as it did at its peak. Are we exactly at the midpoint of cosmic light? Not quite. We're a bit past it. The golden age of light lasted for billions of years, but our current time is best described as the late afternoon of the universe's brightness. There are still billions of active stars, but the balance is shifting toward cooler, dimmer populations. Over the next billions to trillions of years, this decline will accelerate as galaxies stop forming new stars entirely. The future of cosmic light is not hard to guess. Big blue and white stars will die quickly when star formation stops, leaving only red dwarfs and stellar remains that will last a long time. Red dwarfs are very efficient, but they give off a lot of dim IR light that humans can't see. They are going to keep the universe burning dimly for a very long time, but not nearly as brightly as it does now. Once the last red dwarfs turn into black dwarfs, there will be nothing but dark space. The only sounds that will come from black holes evaporating or stars colliding in the distance. But why does it matter if we're in the middle of the light from space? It tells us how valuable the time we have now is for observing and understanding. Today, galaxies are still bright enough to study, the sky is full of stars at night, and light that traveled billions of years to reach us can still be used to learn about the history of the universe. People who look forward to trillions of years from now will have much darker skies and almost no way to learn about the past of the world. Yes, we are past the center of the light from space. The universe is no longer as bright as it used to be, and the sky at night is not as bright as it was billions of years ago. Future collisions. Will new starbursts briefly reignite the night? The universe is slowly getting darker as fewer stars are being made, but it won't go away until it has a few last bright spots. Although the birth of new stars is slowing down overall, galaxies will continue to crash into each other for billions or even trillions of years, sometimes causing huge starbursts. These amazing events could quickly light up galaxies that would normally be dim, making fireworks in the otherwise quiet sky. So, can future impacts really light up the sky again, even if only for a short time? To understand why collisions matter, consider how galaxies behave today. Most star formation now happens quietly in calm spiral galaxies like the Milky Way. But when galaxies collide, their gas clouds are violently compressed, rapidly collapsing into new stars. These bursts can form thousands of stars per year, compared to just a few in normal conditions. Some of the brightest galaxies in the universe, like the Antennae galaxies and ARP 220, are the result of recent collisions that triggered such starbursts. Things will go the same way again. The Milky Way and the Andromeda galaxy are going to crash into each other. They will start to merge into one big circular galaxy in about 4 to 5 billion years. This galaxy is sometimes called Milkomeda. Simulations show that when this happens, huge waves of gas will crash into each other, setting off a very active starburst. The new galaxy will be lit up for a short time by dozens of huge blue stars that are very bright but don't last long. For the next few million years, the night sky will be amazing because it will be full of bright new stars. This is only a blink in the grand scheme of things, but it will be a spectacular one. But this won't be the last such collision. Even after Milkomeda forms, smaller galaxies like the Triangulum galaxy and satellite dwarf galaxies will eventually merge into it, possibly sparking smaller bursts of star formation. Over trillions of years, galaxy mergers will continue, though they will grow less frequent as dark energy pushes galaxies farther apart. The real question is how long these kinds of starbursts can last. To make stars, cold gas is needed, but there isn't enough of it right now. This is because most of the gas in galaxies is either locked up in stars or burned up so much that it can't fall back down. More of the gas that is still there is used up in each crash. This means that future starbursts will be smaller and less common. The impact between the Milky Way and Andromeda is expected to be one of the last really big explosions in our part of the universe. As galaxies merge into massive ellipticals, almost no cold gas will remain to trigger new star formation. Collisions will still happen, but they will mostly involve stellar remnants, white dwarfs, neutron stars, and black holes, rather than gas-rich galaxies. These mergers won't reignite star formation. Instead, they'll produce gravitational waves or rare high-energy events, such as neutron star collisions. The era of bright starbursts will be long over. So, will more crashes briefly light up the night again? Sure, but only for a little while. Over the next few billion years, galaxy collisions will continue to make short-lived bursts of brightness that will temporarily stop the universe from slowly getting darker. Anyone who is living when the Milky Way and Andromeda join will see more stars at night than ever before. But in the big picture of the universe's history, these starbursts are just short-term sparks in a fire that is going out. They happen less often and with less force over time. The ultimate isolated future when galaxies drift beyond reach. At this moment, the night sky looks like a treasure map. Each galaxy is an island of stars spread out across the universe. But soon this view will be gone. Dark energy is making the universe grow faster and faster. Eventually, this speeding up will push galaxies so far apart that we will no longer be able to see most of them. In the far future, the universe will be a lonely place where galaxies, and even whole groups of galaxies, will be cut off from each other forever. The expansion of the universe has been happening since the Big Bang, but for billions of years, gravity slowed it down. Galaxies pulled on each other, forming clusters and filaments of the cosmic web. That changed about 5 billion years ago, when dark energy overtook gravity as the dominant force. Now the universe's expansion is accelerating, and every second, distant galaxies move farther away from each other faster than before. This acceleration has a dramatic consequence for what we can see. Light from distant galaxies is stretched by the expansion of space, making them appear redder, a process called redshift. The farther away a galaxy is, the more its light is stretched. At some point, galaxies move away so fast that their light never reaches us. It's pulled away faster than it can travel across space. Already, some of the most distant galaxies we can observe are close to this cosmic horizon, the ultimate boundary of what's visible. This effect will only grow stronger. In a few trillion years, galaxies beyond our local group will move so far away that their light will never reach us again. To future observers, if any exist, the universe will look almost empty. They will see only their own galaxy or a small group of nearby galaxies bound together by gravity. Everything else will have vanished beyond the cosmic horizon, leaving no evidence that the broader universe ever existed. Not only will this make the world look different, but it will also change how we think about it. We can now study the cosmic microwave background, look at billions of galaxies, and piece together the past of how the universe has changed over time. But people who live trillions of years from now won't have those hints. Astronomers call the place where they live a cosmic island. There is no way for them to know that other galaxies used to be close by. If they can't see any signs of growth, they might even think that their single galaxy is the whole universe. Locally, things will still happen. The Milky Way and Andromeda will merge into the giant elliptical galaxy Milkomeda within about 4 to 5 billion years. Smaller satellite galaxies will eventually merge into it as well. But beyond this local group, no new galaxies will ever arrive. The accelerated expansion will tear large-scale structures apart, making each galactic group a lonely island in an ever-growing dark ocean. This final separation will also change how stars form in the future. As galaxies get farther apart, they will no longer be able to join and create bursts of new stars. As soon as there is no more gas left, there will be no more stars, and the ones that are there will slowly fade away. The world will not only be cut off from everything else, it will also be dark and quiet. It will fully enter the degenerate era, which is ruled by the remains of stars. From a human perspective, this is almost impossible to imagine. The night sky feels eternal, but we live in a unique era when the universe is still accessible to study. We can see billions of galaxies and learn about the Big Bang because their light hasn't yet been pulled beyond our reach. In the far future, that knowledge will be lost forever, erased by the relentless acceleration of space. When will galaxies move so far away that they can't be reached at all? Most galaxies outside of our group will have crossed the cosmic horizon in about 100 billion years. The universe will be lonely by then, with each group of galaxies stuck in its own bubble of space. Before heat death even happens, the universe will feel empty because you won't be able to see its light. The probability of being early observers in cosmic time. From the sky at night, it may seem like this is how things have always been and how they will always be. However, our time here on Earth is very unique and only lasts a short time in the big picture of global history. It seems odd that smart beings like us exist now, when the universe is still young and full of stars, instead of trillions of years from now, when time has been stretched out for a much longer time. Why are we here so early in the history of the universe? The early observer problem is what scientists call this puzzle. Despite only being 13.8 billion years old, the universe will last for many, many more years. There is a lot more time in the future than in the past, so if life could change at any time, you might think that the smartest societies would appear much later. That might not be true though, and that's why our time is so strange. First, consider the conditions needed for life. Life requires stable stars, planets rich in heavy elements, and a relatively calm cosmic environment. Those ingredients weren't available early on. For the first few billion years, galaxies were chaotic and violent, filled with supernovae and massive black hole activity that constantly bombarded planets with lethal radiation. There also weren't enough metals to form rocky planets like Earth. Only after multiple generations of stars enriched the universe with carbon, oxygen, and iron could habitable worlds become common. That process peaked about 8 to 10 billion years after the Big Bang, which is exactly when we find ourselves living. Second, the future may not be as life-friendly as it seems, despite the universe having trillions of years left. While stars will continue forming for a long time, most of the stars forming now and in the future will be red dwarfs. These tiny, long-lived stars burn for trillions of years, but they are not perfect for life. Many emit violent stellar flares that can strip away planetary atmospheres, leaving worlds barren. Even if life adapts to such conditions, intelligent life might be rare around these stars, making now, during the era of stable, metal-rich sun-like stars, the most probable time for complex life to emerge. There's also the matter of being seen and being known. We are lucky to live in a time when galaxies are still close enough to study. Most galaxies will be beyond the visible range in 100 billion years because of cosmic expansion. This will make it look like the universe is empty to people in the future. People who lived back then might not have known about other galaxies or even the Big Bang. If intelligence appears later, those beings will be locked in island galaxies where they will not know the truth about the world. Today, on the other hand, is one of the few times in history when the universe is still bright and easy to study. Statistically, this timing makes sense if intelligent civilizations depend on two things: enough time for life to evolve, and the right physical conditions for that life to thrive. The best overlap of these factors happens now, in this mid-era sweet spot. Early in the universe, planets were rare. Far in the future, star formation will slow, habitable worlds will become scarcer, and radiation environments will be less favorable. This idea is backed up by the Drake equation, which guesses how many societies there might be. There should be a lot of intelligent life in the universe around this point in time, just a few billion years after the universe's metal content reaches its highest point. Even though we are not at the beginning of the universe's history, we are at the beginning of the time when it is possible for life to exist. Are we early observers in the history of the universe? In terms of how long the world has been around, yes, we are very young. On the other hand, we are living in the best time for learning about life and the universe. The world is still full of stars and planets, and the cosmos is open for discovery. This is a rare and special time. In billions or trillions of years, if there is intelligent life at all, it might never know how beautiful and bright the universe used to be. The stars will go out one day, galaxies will move out of reach, and even the most powerful black holes will disappear. But we are not there yet. We are lucky to live in a time when the sky is still bright, full of stars, and ready to be explored. Many, many years from now, no one will be able to see or understand the universe the way we do. It doesn't matter if we are at the start, the middle, or the end of time. We are the lucky ones who can see the universe's best part while it is still happening.